Hello there, and welcome to Nightfall Science. Tonight, we drift beyond Earth in search of life among the stars. Let your shoulders soften and your thoughts grow quiet. The universe waits. Let's begin. Earth remains the only world where life is known to exist. From space, our planet appears as a small sphere of blue and white. Oceans cover most of its surface. Clouds move quietly through its atmosphere. Green forests gather sunlight, while microscopic organisms fill the water, soil, and air. Every confirmed living thing belongs to this single world. This does not mean that Earth is necessarily the only living planet. It simply means that life elsewhere has not yet been confirmed. No distant signal has been proven to come from another civilization. No spacecraft has found an organism on another planet. No telescope has detected a chemical signature that can only be explained by biology. For now, Earth is the one example available. That single example is wonderfully diverse. Life includes trees, whales, fungi, insects, coral, and countless forms too small to see. It exists in warm sunlight and deep underground. It floats through the atmosphere and settles beneath the ocean floor. Yet all known organisms share a deep chemical relationship. They use carbon-rich molecules. They depend on liquid water. They store information in genetic material. They build cells from many of the same basic ingredients. This shared chemistry suggests that every living creature belongs to one ancient family. A blade of grass, a drifting jellyfish, and a human being carry distant echoes of the same beginning. Scientists study this family to understand what life requires. Biology reveals how organisms grow and adapt. Chemistry shows how simple molecules can form complex structures. Geology preserves traces of ancient environments. Astronomy reveals where similar conditions may exist elsewhere. The search begins by looking closely at home. Earth is not only the place where the question is asked, it is also the first quiet clue toward an answer. Life appears very early in Earth's long history. The planet forms about 4.5 billion years ago. Its beginning is warm and restless. Material collides and gathers. Volcanoes reshape the young surface. Asteroids and smaller objects continue to arrive. Over time, the outer layers cool, a solid crust develops. Water collects, and ancient oceans begin to settle into low regions. The exact moment when life begins remains unknown. Rocks from Earth's earliest ages are rare. Many have been melted, buried, or transformed by geological activity. The oldest chapters have been folded back into the planet. Even so, ancient rocks preserve several possible signs. Scientists examine microscopic structures that resemble cells. They study layered formations called stromatolites, which can be produced by communities of microbes. They also measure different forms of carbon trapped inside minerals. Living organisms often process carbon in recognizable ways, leaving subtle chemical patterns behind. Widely accepted evidence shows that life is present more than 3.5 billion years ago. Some studies suggest that biological activity may reach farther back, perhaps close to 4 billion years. Those earlier signs remain difficult to interpret, so researchers approach them carefully. Whatever the precise date, life seems to emerge relatively early in Earth's history. Once stable water and suitable chemistry become available, biology appears within a comparatively small part of geological time. For billions of years, most life remains microscopic. Single-celled organisms transform oceans, rocks, and eventually, the atmosphere. Their work is quiet, but immense. They cycle carbon, release gases, and build communities layer by layer. Complex animals arrive much later. Forests and flowering plants appear later still. Human beings occupy only the thinnest final line of the timeline. The oldest story of life is therefore not a story of large creatures. It is a story of tiny cells drifting through ancient water. In those early oceans, Earth begins its long experiment with being alive. Life survives in places that once seemed almost unlivable. Some organisms grow in intensely salty lakes. Others remain active in acidic water. Microbes live inside rocks, beneath ice, and far below Earth's surface. Entire communities gather around openings in the deep ocean, where warm, mineral-rich water rises from the sea floor. These organisms are often called extremophiles. The name describes life adapted to conditions that seem extreme from a human perspective. Some prefer high temperatures. Others grow best in freezing environments. Certain microbes tolerate strong radiation or immense pressure. Some obtain energy without using sunlight at all. This discovery expands the idea of a habitable world. For a long time, life is easily imagined only on a planet resembling the familiar surface of Earth. Such a world has gentle sunlight, open water, and a comfortable atmosphere. These conditions remain important, but they are no longer the only possibilities. Deep beneath the ocean, sunlight disappears completely. Plants cannot perform photosynthesis there. Yet microbes use chemical reactions involving minerals and gases. Other organisms gather around them, forming ecosystems supported by energy from within Earth. Life does not ignore the laws of chemistry. It still requires usable energy and suitable materials, but it uses those materials in remarkably varied ways. A frozen moon may therefore hide a living environment beneath its ice. A dry planet may preserve microbes underground, protected from conditions at the surface. A distant world may support chemistry unlike anything found in a forest or shallow sea. Extremophiles do not prove that such places contain life. They reveal that habitability can take more than one form. They also change the emotional shape of the search. Empty-looking landscapes are no longer dismissed so quickly. A sheet of ice may cover an ocean. A dark cave may contain slow metabolism. A grain of stone may shelter a tiny community. Life often occupies narrow spaces between heat and cold, water and rock, stillness and change. The smallest organisms quietly teach astronomy to search more widely. The ingredients of life are woven throughout the cosmos. Life on Earth depends heavily on 6 elements. They are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Together they are sometimes remembered by the shortened name, CH-NOPS. Hydrogen forms during the early universe. Many heavier elements form later inside stars. Carbon, nitrogen, and oxygen are produced through stellar processes. Other events, including stellar explosions, spread enriched material outward into space. The atoms inside living cells, therefore, have histories older than Earth. Carbon moves through blood, leaves, oceans, and the atmosphere. Calcium supports bones and shells. Iron helps carry oxygen through the body. These elements do not begin as biological material. They become part of life only after long cosmic and planetary journeys. Space also contains organic molecules. In chemistry, the word organic usually refers to compounds built around carbon. It does not automatically mean that a living organism produced them. Scientists find organic material in meteorites. Some meteorites contain amino acids, which life uses to construct proteins. Researchers have also identified nucleobases and other carbon-rich compounds related to biological chemistry. Asteroids can therefore act as natural laboratories. Water, minerals, and simple carbon compounds interact within them over immense periods. Pieces eventually fall toward planets, carrying some of this chemistry to new environments. This does not show that life arrives fully formed from space. It shows that part of life's molecular preparation can occur beyond a planet's surface. The same broad ingredients appear in interstellar clouds, comets, moons, and young planetary systems. Nature repeats familiar chemistry across enormous distances. A distant planet does not need to create carbon or oxygen from nothing. Those atoms are already part of the material from which planets form. The question is whether they gather in the right environment, with liquid, energy, stability, and time. Across the dark between stars, the universe quietly carries the pieces from which living worlds may grow. Mars preserves the memory of a wetter world. Today, its surface is cold and dry. Its atmosphere is thin, and liquid water cannot remain stable across most open ground for long. Rust-like minerals give the planet its familiar reddish color. Yet Mars has not always looked this way. Spacecraft observe valleys that resemble ancient river channels. They photograph deltas where flowing water once carried sediment into lakes. Rovers examine rounded stones, layered rocks, and minerals that form through contact with water. These features reveal that ancient Mars contains rivers, lakes, and long-lasting wet environments. Its atmosphere is once thicker, and parts of the surface are warmer than they are today. One especially important place is Jezero Crater. A river once enters this basin and builds a broad delta. NASA's Perseverance rover explores the region because deltas on Earth often preserve organic matter and traces of ancient environments. Another rover, Curiosity, studies rocks inside Gale Crater. Its observations show that a lake exists there in the distant past. The water has chemical conditions that could have supported microbial life as it is understood on Earth. Habitability, however, is not the same as habitation. A lake can contain suitable water, minerals, and energy without ever developing organisms. Scientists therefore search for patterns that might record past biology, while also studying non-living chemistry that can produce similar patterns. Care is essential. Organic molecules are interesting, but they can form without life. Unusual minerals are useful clues, but geology can create many unexpected shapes. A convincing discovery requires several lines of evidence agreeing with one another. Mars may also preserve material better than Earth. Our planet continually reshapes its surface through oceans, weather, and moving crust. Mars changes more slowly. Some ancient rocks remain exposed for billions of years. If microbes once live in Martian lakes, traces may still rest inside those quiet layers. The red planet is not merely a dry neighbor. It is an old world holding the faded outlines of rivers. Europa may hide more liquid water than Earth beneath its ice. Europa is one of Jupiter's largest moons. Its surface is bright, frozen, and crossed by long dark lines. Few large mountains or deep ancient craters interrupt the pale landscape. Below that icy shell, evidence points toward a global ocean of salty water. One of the strongest clues comes from NASA's Galileo spacecraft. During close passes of Europa, its instruments measure the moon's response to Jupiter's changing magnetic field. The observations are best explained by an electrically conducting layer beneath the surface. Salty liquid water is a natural explanation. Scientists estimate that Europa's hidden ocean may contain around twice as much water as all Earth's oceans combined. The ocean remains liquid partly because Europa is gently flexed by gravity. The moon travels around Jupiter in a slightly stretched orbit. Jupiter's pull changes as Europa moves closer and farther away. This repeated bending produces internal heat. The surface stays extremely cold, but warmth from within may help maintain the ocean. Water alone is not enough for life. A suitable environment also requires useful chemistry and a steady source of energy. Europa may offer all three. Its ocean probably touches a rocky seafloor. If water interacts with warm rock, chemical reactions could release energy and nutrients. Similar interactions support ecosystems near some hydrothermal environments on Earth. Material from the surface may also move downward through cracks or slowly shifting ice. Radiation near Jupiter alters surface compounds, creating new chemicals. If some reach the ocean, they may contribute additional energy. No organism has been detected there. Europa's habitability is still being investigated. The ice hides its ocean from direct view, and many important details remain uncertain. Yet its frozen surface may cover a stable sea that has existed for much of the solar system's history. Beneath Jupiter's quiet moonlight, an unseen ocean continues moving in the dark. Enceladus sends samples of its hidden ocean into space. This small moon circles Saturn beneath a surface of clean, bright ice. It is only about 500 kilometers wide. At first glance, it seems too small and cold to remain geologically active. Then the Cassini spacecraft observes something remarkable. Near Enceladus's south pole, long fractures cut across the surface. Water vapor and grains of ice rise through these openings. They form enormous plumes that extend into space and supply material to Saturn's faint E-ring. The moon is releasing part of its internal ocean. Cassini flies through the plume several times. Its instruments examine the ejected particles and gases without needing to land or drill through the ice. The samples reveal water, salts, organic compounds, and tiny silica particles. The silica is especially informative. Its properties suggest that warm water interacts with rock inside Enceladus, much as water circulates through hydrothermal systems on Earth. Molecular hydrogen is also detected. It can form when hot water reacts with certain minerals in rock. On Earth, some microbes use hydrogen as an energy source. Later studies identify phosphorus in ice grains from the plume. Phosphorus is essential to known life. It contributes to genetic material, cell membranes, and the transfer of energy within cells. More recently, researchers continue finding a rich collection of organic compounds in Cassini's stored data. These molecules do not demonstrate biology. They show that Enceladus contains active and varied chemistry. The moon appears to possess several major ingredients associated with habitability. It has liquid water, useful elements, organic material, and possible chemical energy. Its ocean also rests against a rocky core. That contact allows water and minerals to exchange material over time. Enceladus offers science a rare gift. A hidden sea usually keeps its secrets beneath kilometers of ice. This moon lifts droplets of its ocean outward, where a passing spacecraft can gather them. Far from the warmth of the sun, a small frozen world quietly scatters pieces of its ocean among Saturn's rings. Ganymede may contain layers of oceans hidden inside the largest moon in the solar system. Ganymede circles Jupiter beyond the orbit of Europa. It is wider than the planet Mercury, although it contains much less mass. Its surface shows two different kinds of terrain. Some regions are dark and ancient, others are brighter, with long grooves shaped by geological movement. Beneath this frozen landscape, strong evidence points toward a vast saltwater ocean. NASA's Galileo spacecraft first provides important measurements of Ganymede's magnetic environment. Later, the Hubble Space Telescope observes faint auroras glowing around the moon. These ribbons of light shift as Jupiter's magnetic field changes. A large ocean of electrically conducting saltwater can explain why the auroras do not move as much as expected. The hidden ocean appears to influence Ganymede's magnetic response. Scientists think the water may rest beneath a thick outer shell of ice. Some models suggest that Ganymede does not contain one simple ocean. Instead, layers of liquid water may alternate with different forms of high-pressure ice. Near the surface, ordinary ice forms the crust. Farther down, pressure changes the structure of frozen water. Its molecules arrange themselves into denser forms. Between these layers, liquid oceans may remain trapped like dark seas inside a frozen world. The total amount of water could be greater than the water found across Earth's surface. Ganymede also possesses its own magnetic field. It is the only moon known to generate one internally. Deep within the moon, moving material around an iron-rich core may create this quiet magnetic shield. Whether the hidden water touches rock remains uncertain. That contact matters because rock can provide minerals and chemical energy. If dense ice separates the ocean from the rocky interior, the environment may receive fewer useful ingredients. Even so, Ganymede expands the number of possible ocean worlds. It shows that large reservoirs of water can remain hidden far beyond the warmth that reaches Earth. Inside Jupiter's largest moon, water may rest in several quiet layers, folded between sheets of ancient ice. Callisto may shelter an ocean beneath one of the oldest surfaces in the solar system. Callisto is another of Jupiter's 4 large moons. It travels farther from the planet than Io, Europa, and Ganymede. From a distance, its surface resembles a pale stone covered with countless marks. Those marks are impact craters accumulated over immense spans of time. Callisto does not appear to recycle its surface as actively as Europa. It has no broad network of young ice ridges. It shows little evidence of recent internal reshaping. Much of its landscape preserves the long history of objects striking the outer solar system. One enormous feature is called Valhalla. Bright rings spread around its center for thousands of kilometers. They form after a large impact sends waves moving through Callisto's icy crust. For many years, this old and quiet moon seems less interesting as a possible habitat. Then measurements from the Galileo spacecraft suggest that an electrically conducting layer may exist beneath its surface. A salty underground ocean could produce such a signal. Models place this water deep below the crust, perhaps beneath more than 100 kilometers of ice. The exact thickness is uncertain. Its ocean may also be less active than those of Europa or Enceladus. Life requires more than water. It needs a continuing source of energy and access to useful chemistry. A deeply buried ocean that rarely interacts with rock or surface material may provide fewer opportunities, yet even a quiet ocean remains important. Callisto demonstrates that liquid water may survive inside worlds that appear geologically still. Radioactive elements in rock produce heat as they slowly decay. Dissolved salts lower the temperature at which water freezes. Thick ice above the ocean acts as insulation, helping warmth remain inside. These modest processes can preserve liquid across billions of years. Callisto therefore broadens the meaning of an ocean world. Not every hidden sea needs bright plumes or freshly fractured ice. Some may remain enclosed, stable, beneath the solar system's most heavily cratered moon. An ancient ocean may be resting without a ripple of light. Titan has rivers, rain, lakes, and seas made from liquid hydrocarbons. Saturn's largest moon is wrapped in a thick golden atmosphere. The haze hides its surface from ordinary cameras. Before the Cassini-Huygens mission arrives, many details of the landscape remain unknown. Radar gradually reveals a world shaped by flowing liquid. Dark lakes gather near Titan's poles. Broad seas stretch across low regions. Channels wind toward their shores. Rounded stones observed by the Huygens lander suggest that liquids have moved across the ground, yet the surface is far too cold for open liquid water. Titan's rivers and lakes contain methane and ethane. These substances are gases under ordinary conditions on Earth. On Titan, temperatures near -179 degrees Celsius allow them to remain liquid. Methane moves through a cycle that resembles Earth's water cycle. It evaporates from lakes and seas. It enters the atmosphere and gathers into clouds. Rain falls onto hills and plains. Streams carry the liquid back toward lower ground. Seasonal changes alter the clouds and rainfall. Storms can darken wide areas of the surface. Over time, flowing hydrocarbons carve valleys and reshape shorelines. Water plays a different role on Titan. At its surface temperature, water behaves like solid rock. Mountains and bedrock can be made largely from water ice. Methane flows across this frozen foundation, as water flows across stone on Earth. The result feels familiar and unfamiliar at the same time. Titan has weather, coastlines, dunes, and changing seasons. Yet every part of this landscape follows a colder version of chemistry. Rain has a different scent and composition. Ice forms the ground. Sunlight reaches the surface as a dim amber glow. No life has been found in Titan's lakes. Known biology requires liquid water, and no Earth organism is known to live in liquid methane. Still, Titan offers a natural laboratory for asking how chemistry behaves inside a liquid, unlike the oceans of Earth. Under Saturn's distant light, methane rain quietly completes its journey from cloud to sea. Titan's atmosphere produces complex organic molecules before they settle onto the surface. The atmosphere is mostly nitrogen, with methane forming a smaller but important part. High above the ground, sunlight and energetic particles break some of these molecules apart. The fragments begin joining in new ways. They create a wide family of carbon-rich compounds. Some remain as gases, others grow into larger particles that drift downward through the atmosphere. Together, these particles form Titan's orange haze. Over long periods, organic material settles across dunes, plains, lakes, and icy highlands. Titan's dark equatorial dunes may contain grains made partly from this atmospheric chemistry. They rise into long parallel shapes, guided by winds moving around the moon. Some dune fields extend across areas comparable to large regions on Earth. The word organic does not mean that these compounds are alive. It simply describes chemistry based mainly around carbon. Many organic molecules form naturally, without any biological activity. Even so, carbon chemistry is central to life on Earth. Titan allows scientists to study how complex molecules develop in a cold atmosphere. Some reactions may resemble steps that occur on the early Earth before biology begins. The environment can therefore reveal how simple ingredients gradually become more elaborate. Titan may also contain a deep ocean beneath its icy crust. Measurements of its rotation, gravity, and surface movement support the presence of an internal liquid layer, probably composed of water mixed with substances such as ammonia. The organic-rich surface and the water-rich interior may normally remain separated. Impacts, fractures, or episodes of internal activity might sometimes bring their materials closer together. Large impact craters are especially interesting. Heat from an impact can temporarily melt water ice. Organic compounds from the surface may then mix with liquid water, creating a short-lived environment for complex chemistry. No evidence shows that this process has produced life. It does show that Titan contains many of the ingredients needed to study the pathways leading toward biology. Its atmosphere works slowly, building molecules and letting them fall like an endless, delicate snow. Venus may once have been more similar to the early Earth. Venus is almost the same size as Earth. It has a rocky body, volcanic landscapes, and an atmosphere filled mainly with carbon dioxide. Today, its surface is extremely warm and covered by immense atmospheric pressure, yet the planet's ancient history may be different. Some climate models suggest that young Venus could have supported liquid water on its surface. If its early rotation, atmosphere, and cloud cover allowed enough heat to escape, shallow oceans may have remained stable for long periods. Other models produce a warmer beginning, with water disappearing much earlier. The available evidence does not yet reveal which history is correct. Venus has been heavily reshaped by volcanic and geological activity. Much of the surface appears relatively young compared with the planet itself. Older rocks that might preserve traces of ancient water are difficult to identify from orbit. The atmosphere provides another clue. Venus contains far more deuterium relative to ordinary hydrogen than Earth does. Deuterium is a heavier form of hydrogen. Ordinary hydrogen escapes into space more easily. The elevated ratio suggests that Venus loses a substantial amount of water over its history. If the planet once has oceans, they gradually evaporate as the climate warms. Water vapor rises into the atmosphere. Sunlight separates water molecules, and hydrogen slowly escapes into space. Today, droplets of sulfuric acid form thick cloud layers. At certain altitudes, the temperature and pressure are more moderate than at the surface. This has led scientists to consider whether microscopic organisms could possibly persist inside cloud droplets. The idea remains highly uncertain. The clouds are extremely dry and strongly acidic. Both conditions present major challenges to life as it is known. Claims about phosphine gas in the atmosphere have also remained debated. Several observations and analyses produce different conclusions. Phosphine can be associated with biology on Earth, but it is not proof of biology, especially when the measurement itself remains uncertain. Venus teaches the search for life to examine both possibilities and limits with patience. Behind its bright clouds, the planet preserves a quiet question about how two neighboring worlds can begin alike and grow so different. Ceres contains salts and signs of briny liquid beneath its surface. Ceres is the largest object in the asteroid belt between Mars and Jupiter. Its rounded shape earns it the title of dwarf planet. It is much smaller than Earth's moon, yet its interior contains a surprising amount of water ice. NASA's Dawn spacecraft enters orbit around Ceres in 2015. It observes dark terrain marked by craters and scattered bright patches. The most famous bright deposits appear inside a Kota crater. At first, these spots shine strongly against the surrounding ground. Detailed measurements show that they contain salts, especially sodium carbonate. Similar minerals can form when salty water rises, reaches the surface, and leaves dissolved material behind as the liquid disappears. The central bright region is called Cerulea Facula. It sits inside a depression near the middle of the crater. Fractures and small domes suggest that material has moved upward from below. A Kota forms after a large impact roughly 20 million years ago. The collision heats the crust and creates temporary reservoirs of melted material. Evidence suggests that deeper brines may also feed later activity. Some bright deposits are geologically young. This indicates that salty liquids may have reached the surface long after the original crater formed. Ceres also contains organic compounds. Dawn detects carbon-rich material near Onutek crater. The concentration appears stronger than expected from a thin coating delivered by an impact, raising the possibility that at least some of the material originates within Ceres. The dwarf planet is colder today than it is in its early history. Most liquid has frozen. Remaining brines are concentrated with salts, which allow them to stay liquid at lower temperatures. Modern Ceres is not considered a likely surface habitat. However, its past may include periods when water, rock, organic compounds, and internal heat interact more actively. It represents a middle ground between rocky asteroids and icy worlds. Even a small body can preserve water and chemistry across billions of years. Size alone does not decide whether a world becomes interesting to astrobiology. In the darkness between planets, Ceres holds bright mineral traces left behind by water that once moved beneath the ground. Comets carry ancient water and organic chemistry through the solar system. A comet begins as a mixture of ice, dust, rock, and frozen gases. Many form in the colder outer regions around the young sun. Some remain there for billions of years, preserving material from the solar system's earliest stages. When a comet approaches the sun, its surface warms. Ice changes directly into gas and escapes. Dust travels outward with it, creating a glowing coma around the nucleus. Solar radiation and the solar wind stretch this material into long tails. The tail can extend for millions of kilometers, while the solid nucleus remains comparatively small. Spacecraft have visited several comets. ESA's Rosetta mission travels alongside Comet 67P, a dark object shaped like two connected lobes. Its instruments detect water vapor, carbon dioxide, carbon monoxide, and many organic compounds. The Philae lander also identifies carbon-based molecules on the surface. NASA's Stardust mission passes through material surrounding Comet Wild 2. It captures tiny particles inside a lightweight substance called aerogel and returns them to Earth. Laboratory analysis reveals minerals and organic material formed under varied conditions. Comets do not contain living organisms, as far as observations show. They contain ingredients and records. During the early solar system, impacts occur much more frequently than they do today. Comets and water-rich asteroids strike the young planets. They may deliver part of Earth's water and some of its organic molecules. Measurements suggest that many asteroids are a better match for Earth's water than the comets studied so far. The source is probably not one simple population of objects. Earth's oceans may gather from several reservoirs, including material already present during the planet's formation. The important idea is that young worlds do not develop in isolation. Planets exchange material with surrounding space. Impacts bring minerals, water, and carbon compounds. Other impacts send pieces of planetary crust outward again. Chemistry travels between worlds long before spacecraft begin making the same journey. A comet's glowing tail is only the visible edge of an ancient parcel carrying memories of the solar system's beginning. Pieces of rock can travel naturally from one planet to another. Large impacts release enormous amounts of energy. When an asteroid strikes a planetary surface, fragments of rock can be thrown upward at high speed. Some travel fast enough to escape the world's gravity. These stones then enter independent orbits around the Sun. Over thousands or millions of years, a small number cross the path of another planet. They move through the atmosphere and fall as meteorites. Scientists know that pieces of Mars have reached Earth. Martian meteorites contain trapped gases whose composition matches the atmosphere measured on Mars. Their minerals and ages also record a history different from ordinary Earth rocks. Most spend millions of years traveling through space before arriving. This natural exchange raises an interesting possibility called lithopanspermia. The word describes the transfer of living material inside rocks between planets or moons. Microbes buried deep within a stone might receive some protection from radiation. Certain organisms and spores can survive intense conditions for limited periods in laboratory experiments. Rock ejected by an impact may also experience lower internal temperatures than its surface, depending on the details of the collision. A successful transfer would require several difficult steps. An organism must survive the original impact. It must endure a long journey through cold space. The rock must enter another atmosphere and reach the surface. Finally, it must arrive in an environment where growth is possible. No evidence confirms that this has happened. Yet the laws of physics allow rocks to move between worlds. If life begins on ancient Mars while Earth is also young, biological material may theoretically travel in either direction. This complicates the meaning of a future discovery. If Martian life shares deep similarities with Earth life, it may represent a second beginning. It may also point toward a shared ancestor carried between the planets. A truly independent form of life would provide stronger evidence that biology begins easily. For now, the idea remains a carefully studied possibility rather than a known history. Across the solar system, stones drift between planets, carrying chemistry and perhaps preserving stories that have not yet been read. The solar system contains many environments where the ingredients of life gather in different ways. Earth places liquid water on its surface beneath a mild atmosphere. Mars preserves dried lake beds and ancient river deltas. Europa and Ganymede hide oceans beneath ice. Enceladus releases part of its ocean into space. Titan covers its ground with organic material and fills its lakes with methane. Venus carries clues to water that may have disappeared. Ceres preserves salts left by underground brines. Asteroids and comets transport carbon-rich chemistry from one region to another. None of these environments has yet provided confirmed evidence of extraterrestrial life. Their importance lies in what they reveal about habitability. Water is not restricted to Earth. Organic compounds are not rare. Energy can come from sunlight, chemical reactions, radioactivity, gravity, and internal heat. Planets and moons continue changing long after they form. The search is therefore no longer focused only on a perfect copy of Earth. Some habitats may rest beneath frozen surfaces. Others may exist briefly after an impact. A planet may be habitable during one era and quiet during another. A moon may support chemistry in darkness, far beyond the traditional region where surface water remains liquid. This variety encourages careful imagination. Life elsewhere may use familiar carbon chemistry in an unfamiliar setting. It may remain microscopic for its entire history. It may begin and disappear before a spacecraft ever arrives. It may never begin at all, even where every expected ingredient seems present. Each possibility teaches something about the relationship between matter and biology. The local solar system is only one planetary family. It formed from one cloud, around one star, during one period of cosmic history. Its worlds share many ingredients and part of the same past. Beyond the Sun, the Milky Way contains hundreds of billions of other stars. Many are surrounded by planets. Their systems have different ages, arrangements, temperatures, and chemical histories. The search for life begins close to home, because nearby worlds can be reached and studied in detail. Yet the question eventually moves outward, toward points of light separated by years of travel. Our solar system offers several quiet laboratories. The wider galaxy offers an ocean of possibilities. Planets are not unusual companions to stars. For much of human history, the planets of the solar system are the only worlds known. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune move through the sky while the distant stars appear fixed behind them. Astronomers naturally wonder whether those stars also possess planets. The idea is ancient, but evidence takes a long time to arrive. A planet does not produce much visible light of its own. It usually reflects only a tiny fraction of the light from its star. From many light years away, the planet appears extremely close to that much brighter star. The difference can be compared to finding a small firefly beside a distant lighthouse. Even large planets are difficult to see directly. Earth-like worlds are smaller, dimmer, and often lost inside the glare of their suns. The first confirmed planets beyond the solar system are discovered during the early 90s. They orbit a pulsar, the dense remnant left by a massive star. Their existence is surprising because such an environment is very different from the gentle planetary system surrounding the Sun. Soon afterward, astronomers find a planet orbiting a star similar to the Sun. These discoveries begin a quiet transformation. New instruments reveal planets around many kinds of stars. Some systems contain one known world. Others contain several planets moving together in closely arranged orbits. Planets appear around young stars, old stars, small stars, and stars brighter than the Sun. Not every star is known to have planets. Yet the evidence suggests that planet formation is a common result of star formation. A young star begins inside a cloud of gas and dust. Material that does not fall into the star gathers into a rotating disk. Dust grains collide and stick together. Small bodies grow into larger ones. Over millions of years, some become planets. The details differ from system to system, but the broad process repeats throughout the galaxy. The night sky is therefore not simply a field of distant suns. Around many of those points of light, unseen worlds are quietly completing their years. The discovery of 51 Pegasi b reveals that planetary systems can be very different from our own. In 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi. The star is located roughly 50 light-years from Earth and resembles the Sun in several important ways. The planet is now known as 51 Pegasi b. It has at least about half the mass of Jupiter, yet it does not move through a wide, cold orbit like Jupiter. Instead, it circles extremely close to its star. 1 year on 51 Pegasi b lasts only a little more than 4 Earth days. This arrangement surprises astronomers. Earlier ideas about planetary formation often assume that giant planets remain far from their stars, where cooler temperatures allow large icy and rocky cores to develop. A giant world so close to its Sun does not fit that simple picture. Researchers eventually develop models of planetary migration. A gas giant may form farther from its star, then gradually move inward through interactions with the surrounding disk or with other planets. 51 Pegasi b belongs to a class of worlds called hot Jupiters. These planets are large and gaseous, but their nearby stars heat them to very high temperatures. Some are tidally locked, keeping one side facing their star while the other remains turned toward space. Their atmospheres can contain powerful winds that carry heat between the two hemispheres. Clouds may form from materials that would remain solid rock on Earth. The upper atmosphere can expand as it absorbs intense stellar energy. Hot Jupiters are not considered promising homes for life as it is known. They are mainly composed of gas, and their environments are unlike the mild surface of Earth. Their scientific value is still immense. They show that planetary systems can rearrange themselves. They reveal that a world's present location does not always mark the place where it formed. The first planet found around a sun-like star does not resemble Earth. Instead, it teaches astronomy that nature builds worlds with greater variety than expected. A planet can reveal itself by passing quietly in front of its star. This event is called a transit. From the correct viewing angle, An orbiting planet moves between its star and a distant telescope. The planet blocks a small amount of starlight. The star appears to dim slightly, then returns to its normal brightness after the planet moves away. The change is usually very small. A large planet may block around 1% of a sun-sized star's light. An Earth-sized planet blocks much less. Sensitive instruments are needed to measure the difference reliably. One dip in brightness is not enough to confirm a planet. Stars can change naturally. Dark star spots rotate across their surfaces. Nearby stars can blend together in a telescope's view. Instrumental effects can also create misleading signals. Astronomers therefore look for a repeating pattern. If the same dimming occurs at regular intervals, it may mark a planet completing one orbit after another. The time between transits reveals the length of the planet's year. The depth of the transit provides an estimate of the planet's size. A larger world blocks more light. A smaller one produces a shallower dip. The shape and duration of the transit also reveal details about the orbit. A transit offers more than the outline of a planet. Some starlight passes through the thin outer edge of its atmosphere before reaching the telescope. Molecules in the atmosphere absorb particular wavelengths. By separating the light into a spectrum, astronomers can search for these patterns. Water vapor, sodium, methane, carbon dioxide, and other substances can leave distinctive signatures. The signals are faint, but they offer a way to study the air of a world that cannot be visited directly. Most planetary systems are not aligned so that their worlds transit from Earth's viewpoint. Many planets therefore remain invisible to this method. Yet when the geometry is right, a distant planet creates a delicate rhythm in the light of its star. For a few hours, the world becomes known by the small shadow it carries across the galaxy. A star can also reveal a planet through a gentle gravitational motion. A planet does not truly orbit a perfectly stationary star. The star and planet both move around their shared center of mass. For a small planet, the star's motion is tiny. For a large planet, the effect is easier to measure. As the star moves slightly toward Earth, its light shifts toward shorter wavelengths. As it moves away, the light shifts toward longer wavelengths. This effect is related to the changing pitch of a sound as its source approaches and recedes. Astronomers call this technique the radial velocity method. By measuring the repeated shifting of lines in a star's spectrum, researchers can detect the gravitational influence of an unseen planet. The strength of the motion provides information about the planet's mass. The timing reveals its orbital period. The pattern can also show whether the orbit is nearly circular or more elongated. 51 Pegasi b is discovered through this method. Modern spectrographs are precise enough to measure extremely small stellar motions. They search for changes comparable to the speed of a person walking slowly or cycling gently. Earth causes the sun to move by only a small amount. Detecting a similar planet around another star requires long observations, stable instruments, and careful treatment of the star's own activity. Stars are not perfectly quiet. Their surfaces contain moving gas, magnetic regions, and spots. These features can imitate some of the signals produced by planets. Researchers compare many observations and examine different wavelengths to separate stellar behavior from orbital motion. When a planet both transits and produces a radial velocity signal, the two methods work especially well together. The transit reveals the planet's size. Radial velocity reveals its mass. From both measurements, scientists estimate its density. Density helps distinguish a rocky world from a gas-rich one. A small recurring motion in a distant star can therefore reveal the hidden weight of a planet. Across the darkness, gravity allows worlds to announce their presence without producing a light of their own. The Kepler Space Telescope shows that the galaxy is filled with small planets. Kepler launches in 2009 with a focused purpose. It observes the brightness of more than 100,000 stars in a region of the Milky Way. The telescope watches continuously, searching for transits. Its field of view contains ordinary-looking points of light. For months and years, Kepler measures them with remarkable patience. Each star becomes a long record of brightness. Inside those records, repeated dimming events begin to appear. Some belong to planets larger than Jupiter. Others come from worlds close to the size of Earth. Many systems contain several planets, each producing a different rhythm. Kepler changes the understanding of what is common. Before its mission, large planets are easier to discover because they create stronger signals. This can make giant worlds appear more typical than they truly are. Kepler reveals a rich population of smaller planets. Many are between the size of Earth and Neptune. The solar system contains no planet in this size range, yet such worlds appear frequently around other stars. Some are probably rocky super-Earths. Others may have deep atmospheres and belong to a group often called sub-Neptunes or mini-Neptunes. Their composition cannot be determined from size alone. A planet only slightly larger than Earth can sometimes hold a thick layer of gas. Another may contain a large fraction of water or ice. Kepler also finds tightly packed systems. Several planets may orbit closer to their star than Mercury orbits the Sun. Their years can last only days or weeks. Despite the compact arrangement, many remain stable over long periods. The mission does not observe every star in the galaxy. It studies one portion of the sky and favors planets whose orbits produce transits. Astronomers use statistics to correct for these limitations. The result is a broader conclusion. Planets are abundant, and small worlds are widespread. The discovery of another planet is no longer treated as an unusual exception. Kepler turns isolated findings into a population. In the measured fading of distant stars, the galaxy begins to resemble a vast garden of planetary systems. Some planets have no close equivalent in the solar system. A super-Earth is generally larger than Earth but smaller than Neptune. The name refers mainly to size or mass. It does not mean that the planet is automatically more habitable or more similar to Earth. A super-Earth may be rocky. It may contain deep oceans. It may possess a heavy atmosphere that presses strongly against the surface. It may also resemble a smaller version of Neptune, with a rocky core hidden beneath layers of gas. Mini-Neptunes occupy a related range. These worlds can carry atmospheres rich in hydrogen and helium. Beneath the atmosphere, they may contain water, rock, or high-pressure mixtures, unlike any natural environment on Earth's surface. Because the solar system has no clear example, astronomers build models from indirect measurements. Mass and radius provide average density. Atmospheric spectra reveal some gases. The age and energy output of the star help estimate how much atmosphere a planet may have lost. Two planets of similar size can have very different interiors. One may be dense and rich in iron. Another may hold a large rocky mantle. A third may be surrounded by such a thick atmosphere that its visible surface is only cloud. Some planets are called ocean worlds in theoretical models. They may contain far more water than Earth, perhaps covering the entire surface. At great depth, pressure becomes immense. Water can form unusual solid phases, even while warmer liquid remains above it. A global ocean may therefore rest on high-pressure ice, rather than directly touching rock. This separation could influence the movement of nutrients through the planet. Other worlds may have almost no water at all. Their surfaces could be broad deserts of stone beneath thin skies. The variety is important for the search for life. Earth's size does not guarantee Earth's environment. A comfortable temperature does not guarantee an ocean. An atmosphere does not guarantee breathable air. Each world is the result of its formation, chemistry, orbit, and history. Between Earth and Neptune lies a wide family of planets that the local solar system never happened to create. The habitable zone describes a region where surface water may remain liquid. Around every star, temperature changes with distance. A planet very close to its star receives more energy. A planet farther away receives less. Between these regions, there may be an orbital range where temperatures allow liquid water to exist on a planet's surface. This range is often called the habitable zone. The term is useful, but it does not describe a guaranteed home for life. A planet's atmosphere matters greatly. Greenhouse gases trap heat. Clouds can cool a world by reflecting light or warm it by holding energy near the surface. The rotation rate, ocean coverage, land distribution, and internal geology also shape climate. Earth lies within the Sun's habitable zone and supports broad oceans. The Moon occupies almost the same distance from the Sun, yet it has no thick atmosphere and no stable surface seas. Mars also lies near the outer part of the Sun's habitable region, but its present atmosphere is too thin to keep most surface water liquid. Venus shows the opposite lesson. A planet can receive enough energy for liquid water during part of its history, then develop conditions that remove it. The habitable zone changes with the type of star. A bright star warms planets from farther away. A dim red dwarf has a habitable zone much closer in. As a star ages and changes its brightness, the boundaries can slowly shift. Astronomers sometimes use the phrase continuously habitable zone. It describes orbits where suitable temperatures may persist over very long periods. Time matters because life on Earth evolves gradually. A world that remains mild for only a brief geological interval may have less opportunity for complex biology. Yet even stable surface water is only one possible habitat. Europa and Enceladus lie far outside the Sun's traditional habitable zone, but internal heating keeps oceans liquid beneath their ice. The habitable zone is therefore a guide, not a final answer. It marks a quiet beginning for investigation, a ring of possibility drawn around a distant star. Red dwarf stars may offer some of the most common settings for habitable planets. These stars are smaller, cooler, and dimmer than the Sun. They burn their fuel slowly and can remain stable for immense spans of time. Red dwarfs are also the most common type of star in the Milky Way. Because they are dim, their habitable zones lie close to them. A potentially temperate planet may complete an orbit in only days or weeks. This closeness makes such planets easier to detect. A nearby planet creates a stronger gravitational pull on its small star. Its transit also blocks a larger fraction of the star's light. Both effects help astronomers measure the system. The long lifetime of a red dwarf may provide biology with extraordinary amounts of time. The smallest stars can continue shining far longer than the current age of the universe. A stable planet may have billions or even trillions of years available for slow chemical and biological change. Yet these systems also present challenges. Young red dwarfs can be magnetically active. Their surfaces may release energetic flares. Ultraviolet and X-ray radiation can interact with a nearby planet's atmosphere. Over time, this activity may remove part of the atmosphere, especially if the planet lacks a protective magnetic field or a continuing source of gases. Close planets may also become tidally locked. One side remains turned toward the star, while the other faces away. This once seems likely to create a frozen dark side and an overheated bright side. Climate models show that an atmosphere or ocean can transport heat between the hemispheres. A band of mild conditions may form around the boundary between day and night. Clouds above the bright side may reflect part of the incoming energy. The outcome depends on many details. A red dwarf planet could be dry, airless, and quiet. Another might preserve a dense atmosphere and stable water. Observation is needed to distinguish them. Around the galaxy's smallest stars, habitable conditions may survive through a delicate balance of light, air, water, and time. The TRAPPIST-1 system contains 7 small planets around a single red dwarf. TRAPPIST-1 lies about 40 light-years away. The star is much smaller and cooler than the Sun. It is only slightly larger than Jupiter, although it contains far more mass. 7 known planets move around it. All are close in size to Earth. Their orbits are so compact that the entire system would fit well inside the orbit of Mercury around the Sun. The innermost planet completes a year in less than 2 Earth days. Even the outermost known planet circles its star in less than 3 weeks. Several of the planets receive amounts of stellar energy that allow scientists to consider the possibility of temperate conditions. The worlds are named TRAPPIST-1b through TRAPPIST-1h. Their orbits form a resonant chain. The time each planet takes to circle the star is connected to the periods of its neighbors. Their gravitational pulls create a repeating pattern, almost like several slow rhythms remaining in step. These interactions cause slight changes in the timing of their transits. By measuring those changes, astronomers estimate the planet's masses. When mass is combined with size, density can be calculated. The results indicate that the TRAPPIST-1 planets are broadly consistent with rocky compositions. They are not simply tiny gas giants. Rocky does not necessarily mean Earth-like. Some may have lost their atmospheres. Some may retain dense air. Water could exist as vapor, ice, liquid, or not at all. The star's early activity may have shaped each planet differently. The system is especially useful because several related planets can be compared. They form around the same star and from the same original disk. Differences between them may reveal how distance, radiation, and planetary mass influence atmospheres. Modern space telescopes are beginning to examine their light more closely. The warm inner planets are easier to study first. The cooler worlds require longer observations and subtler measurements. No evidence of life has been found there. Still, TRAPPIST-1 offers something rare, a nearby collection of Earth-sized planets arranged around one small star. 40 light-years away, 7 worlds pass in sequence through the gentle red light of their sun. Proxima Centauri lies a little more than 4 light-years away. It is part of the wider Alpha Centauri system and is currently the closest known star to the solar system. The star is a red dwarf, faint enough that it cannot be seen with the unaided eye. In 2016, astronomers announced evidence for a planet orbiting it. The planet is called Proxima Centauri b. It is detected through the radial velocity method. Its gravitational pull causes the star to move in a small repeating pattern. Proxima b has a minimum mass similar to Earth's and completes an orbit in a little more than 11 days. Because Proxima Centauri is dim, this close orbit places the planet within the region where surface temperatures could allow liquid water. That possibility makes the planet fascinating, but many details remain unknown. Proxima b does not appear to transit from Earth's viewpoint. Its radius is therefore difficult to measure. Without both mass and size, its interior composition cannot be fully determined. Its atmosphere is also unknown. Proxima Centauri produces frequent stellar activity. Flares release bursts of high-energy radiation. Over billions of years, these events may erode an atmosphere. An atmosphere could still survive under certain conditions. A planet may begin with a large supply of gases. Volcanoes may replenish some material. A magnetic field or different atmospheric chemistry may also influence how quickly gases escape. Proxima b is probably tidally influenced by its star. It may rotate slowly or keep nearly the same side facing the light. Climate models show that liquid water remains possible in some atmospheric scenarios, but models cannot replace observation. The planet may be a dry rock. It may hold ice, air, and water. It may resemble nothing in the solar system. Its special quality is not certainty, it is nearness. Even the closest potentially temperate exoplanet remains separated by more than 40 trillion kilometers. Around the nearest neighboring star, one small world waits at the edge of present knowledge. Kepler-Eichenard 6f is one of the first Earth-sized planets found in the habitable zone of another star. The planet circles Kepler-Eichenard 6, a red dwarf hundreds of light-years away. 4 other known planets orbit closer to the star. Kepler-Eichenard 6f is the outermost member of the system. Its radius is only modestly larger than Earth's. This size suggests that it is likely to be rocky, although its exact mass and composition are not known. One orbit lasts about 130 Earth days. The planet receives less energy from its star than Earth receives from the Sun. Its surface could therefore be cool, unless an atmosphere provides enough warming. When Kepler 186f is announced in 2014, it represents an important step. Earlier planets are found in habitable zones, but many are considerably larger than Earth. Kepler 186f demonstrates that an Earth-sized world can occupy this type of orbit. Its star differs from the Sun. The light is redder and dimmer. Plants, if anything like them existed there, would receive a different spectrum of energy. The color of the sky and landscape would depend on the atmosphere, clouds, and surface materials. These images remain speculative. The transit reveals the planet's size and orbit, not its oceans, weather, or biology. At its great distance, the planet is difficult to study in detail with current instruments. Its atmosphere may remain beyond direct measurement for some time, yet Kepler 186f changes the scale of possibility. It is one example found in a limited survey. Other planets of similar size and temperature are likely to exist throughout the galaxy. Some may orbit quieter stars. Some may possess moons. Some may have stable oceans and active geology. Others may be frozen or airless. The importance of one distant world lies partly in what it represents. Earth-sized planets in gentle orbits are not confined to the solar system. Across hundreds of light-years, another small world moves through a region where starlight may allow water to remain. Atmospheres may eventually reveal whether distant planets are merely temperate or truly alive. A planet's atmosphere is shaped by many processes. Volcanoes release gases from the interior. Oceans absorb and return material. Sunlight breaks molecules apart. Rocks react with air and water. Living organisms can also transform an atmosphere over long periods. On Earth, biology strongly influences the air. Plants, algae, and certain microbes release oxygen through photosynthesis. Other organisms produce methane. Life participates in cycles involving carbon, nitrogen, sulfur, and water. Astronomers search exoplanet atmospheres for gases that might be linked to similar activity. These possible signs are called biosignatures. Oxygen is often discussed because it is abundant in Earth's atmosphere and closely connected to photosynthesis. Yet oxygen can also form without life under certain conditions. Sunlight can separate water molecules. Hydrogen may escape into space, leaving oxygen behind. Carbon dioxide can also be broken apart by energetic radiation. Methane can be produced by organisms, but geology creates it as well. A single gas is therefore rarely enough. Scientists look for combinations that remain difficult to maintain together without a continuing source. Oxygen and methane, for example, react over time. If both are abundant, some process must keep replacing them. Even this combination requires caution. The type of star, the planet's oceans, surface minerals, and volcanic activity all matter. Clouds and hazes can hide atmospheric signals. High-altitude chemistry can create patterns that resemble those of life. A planet may also support biology without producing gases that distant telescopes can detect. The most convincing discovery would include several lines of evidence. The planet's temperature and size would be understood. Its star would be carefully studied. Atmospheric gases would form a consistent pattern. Non-biological explanations would be tested and gradually ruled out. The search is not for one magical molecule. It is for a planetary environment whose air, surface, star, and history quietly point in the same direction. In the thin-colored bands of a distant atmosphere, life may someday leave a signature written in light. A possible biosignature must be understood as part of an entire planet. A distant atmosphere can contain oxygen, methane, water vapor, or carbon dioxide. Each gas offers useful information, yet no single molecule provides a simple answer. Planets are complicated chemical systems. Sunlight breaks molecules apart. Volcanoes release fresh gases from the interior. Oceans absorb material and return it later. Rocks react with water and air. Charged particles arrive from the planet's star. All these processes can create or remove gases without the presence of life. Oxygen offers a clear example. On Earth, most atmospheric oxygen comes from photosynthesis. Plants, algae, and certain microbes use sunlight to combine water and carbon dioxide. They store some of the energy in organic material and release oxygen. This makes oxygen an important possible biosignature. However, ultraviolet light can also split water molecules high in an atmosphere. Lightweight hydrogen may escape into space, while heavier oxygen remains behind. A planet could therefore build an oxygen-rich atmosphere without forests, oceans of algae, or living cells. Methane creates a similar challenge. Many organisms on Earth produce methane. It rises from wetlands, sediments, digestive systems, and microbial communities. Geological reactions can also produce it when water interacts with certain kinds of rock. The strongest evidence may come from several gases existing together. Some combinations naturally react and disappear. If they remain present, active processes must continue replacing them. Biology could provide that renewal, although geological explanations must also be examined. The planet's star is part of the evidence. So are its temperature, pressure, age, oceans, clouds, and surface. Researchers therefore build a complete environmental picture. A biosignature is not merely a mark written in an atmosphere. It is a pattern connecting a world's chemistry to its continuing history. Life may announce itself through balance rather than through one extraordinary molecule. A technological civilization could leave traces very different from ordinary biology. These possible traces are called technosignatures. A technosignature is any observable sign that may be produced by technology. It does not need to be a deliberate greeting. It may appear as an unintended result of communication, industry, energy use, or travel. Radio transmissions are the most familiar example. Earth produces radio waves for communication, navigation, science, and radar. Most everyday broadcasts become weak as they spread outward. More powerful and focused transmissions can travel much farther. A distant civilization might use radio for similar reasons. It might also choose an entirely different method. Short pulses of laser light could carry information across interstellar space. Large structures might briefly change the brightness of a star. Industrial activity could alter a planet's atmosphere. Extensive energy use could release additional heat into space. None of these ideas assumes that another civilization follows the exact history of humanity. They begin with broad principles of physics. Technology requires energy. It moves matter. It creates patterns. It may concentrate light into narrow beams or produce chemicals that natural processes rarely maintain. Astronomers search for these differences. A repeating pulse may attract attention because natural sources usually follow other patterns. A radio signal confined to an extremely narrow range of frequencies may suggest artificial engineering. An atmosphere containing unusual manufactured compounds could invite closer study. Every candidate must still be treated carefully. Human technology fills the environment around Earth with signals. Satellites, aircraft, mobile networks, radar systems, and spacecraft all produce interference. Natural objects can also behave in unexpected ways. The discovery process therefore depends on repetition, independent observation, and the gradual removal of ordinary explanations. A confirmed technosignature would reveal more than life. It would show that somewhere, matter has learned to build instruments and reshape its surroundings. Technology may leave only a faint pattern, but a faint pattern can cross the darkness between stars. Radio waves travel through interstellar space with remarkable patience. They are part of the electromagnetic spectrum, alongside visible light, infrared radiation, ultraviolet light, and X-rays. All electromagnetic waves travel at the speed of light in a vacuum. What changes is their wavelength and frequency. Radio waves have longer wavelengths than visible light. Many pass through clouds of interstellar dust that block shorter wavelengths. Earth's atmosphere also allows useful ranges of radio frequencies to reach the ground. This makes large ground-based radio telescopes valuable tools for astronomy. A radio telescope collects waves with a broad dish or an arrangement of many antennas. The incoming energy is extremely faint. Sensitive receivers and computers turn it into measurements that can be studied. Natural radio sources fill the sky. Stars, planets, pulsars, galaxies, gas clouds, and black hole environments all produce radio emission. Most spread energy across a broad range of frequencies or change according to recognizable physical processes. A narrowband signal is different. It concentrates energy into a very small slice of the radio spectrum. Nature rarely produces extremely narrow radio emission. Human transmitters do so easily because focused frequencies are useful for carrying information. This makes narrowband signals interesting candidates in SETI observations. They are not automatically signs of another civilization. Earthly transmitters can enter a telescope from the ground, from aircraft, or from satellites. Reflections can make their origins difficult to identify. Astronomers compare observations from different directions. They examine how a signal changes as Earth rotates. They ask whether it drifts in frequency as a planet moves around a star. A signal from another world may shift gently because its source is rotating and orbiting, just as a distant listener would see Earth's transmissions move slightly in frequency. The radio sky is therefore examined not only for brightness, but for structure and motion. A distant transmission may arrive as an almost invisible line inside a wide ocean of natural sound. Project Ozma begins the modern radio search with two nearby stars. In 1960, astronomer Frank Drake uses a radio telescope at Green Bank in West Virginia. The instrument is 26 meters across and stands among the quiet hills. Drake selects two stars, Tau Ceti and Epsilon Eridani. Both lie relatively close to Earth. Both are single stars with characteristics that make them interesting places to search. At the time, no planets are known around either of them. The project listens near a frequency associated with neutral hydrogen. Hydrogen is the most abundant element in the universe. It naturally emits radio energy at a wavelength of about 21 centimeters. Researchers imagine that another technological society might recognize this frequency as a shared astronomical reference. Project Ozma observes the two stars for many hours. At one point, a strong signal appears while the telescope is directed toward Epsilon Eridani. Excitement gives way to careful investigation. The signal soon proves to be interference connected to human technology. No extraterrestrial transmission is confirmed. The result may appear empty, but the project establishes something important. A scientific search can be performed systematically. Stars can be selected. Frequencies can be examined. Candidates can be recorded and tested. Unusual signals can be separated from ordinary interference. Project Ozma also shows how difficult the task is. The radio spectrum contains countless possible frequencies. A distant civilization may transmit at a frequency no search has chosen. Its signal may be too weak, too brief, or pointed elsewhere. Even a nearby star takes years to exchange a message with Earth. Tau SETI lies almost 12 light-years away. A reply to a transmission would require nearly 24 years for the simplest round trip. Project Ozma listens for only a small moment within that distance and time. Its silence does not close the question. It opens a new scientific practice, allowing the stars to be heard before deciding what they contain. The Drake equation arranges a great uncertainty into a sequence of smaller questions. Frank Drake develops the equation in 1961 while preparing for a scientific meeting at Green Bank. The equation is not a machine that produces one certain number. It is a framework for thinking. It begins with the rate at which suitable stars form in the Milky Way. It considers how many stars possess planets. It asks how many planets may offer environments where life can develop. The later terms become more uncertain. On what fraction of suitable worlds does life actually begin? How often does it develop intelligence? How often does intelligence create detectable technology? The final term asks how long a detectable civilization remains detectable. This last value can change the result greatly. A technological society might produce strong signals for only a short period. It may later become quieter, use focused communication, or change into something that current instruments cannot recognize. Alternatively, a civilization might remain detectable for millions of years. When the equation is created, even the frequency of planets is poorly known. Astronomers have not yet confirmed a single exoplanet around an ordinary star. Today, thousands of exoplanets are known. Surveys show that planets are common, allowing some early terms to be estimated more carefully. The biological and technological terms remain largely open. Earth provides only one example of life beginning. It provides one example of intelligence developing technology. One example cannot reveal how frequently either event occurs. The Drake equation therefore remains valuable because it separates knowledge from uncertainty. Astronomy can improve estimates of stars and planets. Planetary science can examine habitability. Biology can explore the origins and limits of life. History may help researchers think about the duration of technological activity. The equation gathers these fields around one question, without pretending that the answer is already known. It is less like a completed calculation and more like a quiet map of the unknown. Each term marks a doorway through which understanding may slowly enter. The Arecibo message turns a powerful radio transmission into a small portrait of Earth. In 1974, the Arecibo Observatory in Puerto Rico sends a brief message toward the globular star cluster Messier 13. The transmission lasts less than 3 minutes. It uses a sequence of binary information arranged into a simple image. The pattern includes numbers, chemical elements, features related to DNA, a human figure, the solar system, and the Arecibo telescope itself. The message is not a practical attempt to begin a conversation. Messier 13 lies roughly 25,000 light-years away. By the time the transmission reaches the cluster, its stars will have moved from the exact positions they occupied when the message was sent. Any reply would require another journey of about 25,000 years. The transmission instead demonstrates the capability of the upgraded Arecibo radar. It also becomes a thoughtful exercise in communication. How can information be sent without a shared language? Mathematics offers one possible beginning. Quantities and patterns may be recognizable to any observer capable of receiving and analyzing a radio signal. Chemistry offers another shared foundation. Hydrogen and carbon behave according to the same physical laws across the observable universe. Yet even simple images contain assumptions. A distant mind may not arrange the data in the intended dimensions. It may interpret symbols differently. It may sense the universe through methods unlike vision. The Arecibo message therefore reflects humanity as much as its imagined recipient. It shows what people choose to say in a few thousand bits. It turns a species, a planet, and a solar system into a compact pattern of pulses. Arecibo itself can no longer send such a message. Its Great Suspended Instrument platform collapsed in 2020 after structural failures. The transmission continues moving outward. It passes stars and dark clouds, becoming weaker as it expands through space. For thousands of years, a small mathematical portrait of Earth will continue traveling through the Milky Way. The WOW signal remains a famous example of why one unusual observation is not enough. On August 15, 1977, the Big Ear radio telescope in Ohio records a strong narrowband signal. The telescope is conducting a search of the sky for possible artificial transmissions. The signal lasts for the entire 72 seconds that a fixed celestial point takes to pass through the telescope's observing beam. Its intensity rises and falls in a way that resembles a distant source crossing that beam. Astronomer Jerry Amon later examines the computer printout. A sequence of characters marks the changing strength of the signal. Amon circles the sequence in red ink and writes the word "wow" beside it. The name remains. The signal arrives near the frequency associated with neutral hydrogen. It is narrow and strong. These qualities make it interesting, yet the observation contains very little information. Big Ear cannot immediately turn back toward the same place. Its design depends on Earth's rotation carrying different regions of sky through its beam. When the region is observed again, the signal does not return. Later searches also fail to detect a repetition. Many possible explanations are considered. The source may involve human interference, an unusual natural event, or another cause not preserved clearly in the available data. No explanation has become universally accepted. The signal cannot be treated as evidence of extraterrestrial technology because it appears only once. Science requires a candidate to be observed again and examined with other instruments. A repeated signal would reveal whether it stays fixed among the stars. Its frequency drift could be measured. Additional telescopes could confirm that the source is not local interference. None of this becomes possible for the WOW signal. Its importance lies partly in the lesson it carries. An intriguing event may invite attention without supporting a final conclusion. Curiosity and caution can exist together. For 72 seconds, the radio sky creates an unusual line on a page. Then the line fades, leaving behind a question rather than an answer. Light can carry a technological signal as clearly as radio. Optical SETI searches for brief flashes or repeating patterns in visible and near-infrared light. A powerful laser can concentrate energy into a narrow beam. From a great distance, a short laser pulse may momentarily outshine the star around which its source is located. The flash could last only a billionth of a second. Natural objects do produce rapid changes in brightness. However, an extremely short and precisely shaped pulse may stand apart from most ordinary stellar behavior. Special instruments watch for these events. Some divide incoming light among several detectors. A true celestial flash should reach all of them together. An electronic error or charged particle striking one detector would not produce the same shared pattern. Lasers offer several possible advantages. They can carry large amounts of information. Their beams can be aimed toward a chosen star. Their wavelengths can be selected to pass through interstellar dust or planetary atmospheres more effectively. The narrow beam also creates a limitation. A signal aimed elsewhere would pass through the galaxy without crossing Earth. The transmitting civilization would need to select the solar system deliberately, or the beam would need to sweep across many stars. Astronomers also search for continuous laser emission. A distant society might use intense lasers for communication, navigation, power transmission, or the movement of spacecraft. Some of that light could escape into space. No confirmed artificial laser signal has been found. The search nevertheless expands the range of possibilities. Another civilization may not use radio strongly. Its brightest detectable technology may appear in a different part of the electromagnetic spectrum. Optical observations can also be combined with ordinary astronomy. The same telescopes that study stars and galaxies may contain brief signals not originally noticed. Improved software can return to stored data and search for unusual pulses. Across interstellar distance, one carefully shaped flash could carry more meaning than a long and steady glow. Large-scale energy use could warm the space around a civilization. Every machine releases waste heat. A device may convert energy into motion, light, computation, or communication, yet no conversion is perfectly efficient. Some energy eventually spreads outward as heat. This basic principle applies to a small computer and to an entire technological society. If a civilization uses a great amount of stellar energy, part of that energy should eventually emerge as infrared radiation. Astronomers have considered structures that could collect a significant fraction of a star's light. The most familiar concept is often called a Dyson sphere, after physicist Freeman Dyson. The phrase can create an image of one solid shell surrounding a star. A more physically plausible arrangement may involve a vast collection of independent energy-gathering objects moving in separate orbits. Such a swarm could intercept starlight and re-radiate energy at infrared wavelengths. The star might appear unusually dim in visible light, while glowing more strongly in infrared. Natural objects can produce similar patterns. Dust absorbs visible and ultraviolet light, then releases the energy as infrared radiation. Young stars often remain surrounded by dusty disks. Old stars can shed material into space. Galaxies contain clouds where new stars are forming. Researchers must therefore compare any unusual infrared source with detailed natural models. A partial swarm might also cause irregular changes in brightness as structures pass in front of the star. Yet planets, dust clouds, and stellar activity can create complicated dimming as well. No star has been confirmed to host an artificial megastructure. The idea remains useful because it shifts the search from messages to energy. A civilization may never transmit toward Earth. It may still alter the light and heat of its planetary system. At great distances, technology could be visible, not as a voice, but as the gentle warmth left behind by work. A distant atmosphere might preserve traces of industry. Modern technology on Earth produces compounds that were extremely rare before industrial activity. Some manufactured gases remain in the atmosphere for long periods. Certain chemicals interact strongly with infrared light, producing spectral features that telescopes could theoretically detect from far away. Researchers have considered compounds such as chlorofluorocarbons as possible technological atmospheric signatures. On Earth, these gases have been used in refrigeration, manufacturing, and other applications. They are not known to be produced naturally in large quantities. A strong detection on an exoplanet could therefore be interesting. The observation would remain difficult. A distant planet is faint, and its atmosphere forms only a thin layer around it. Clouds may hide part of the spectrum. The star's light can overwhelm the planetary signal. The abundance of the chemical would need to be high enough for the feature to appear clearly. Other forms of technology might alter an atmosphere in different ways. Large-scale combustion changes, concentrations of carbon dioxide and other gases. Artificial illumination produces light on a planet's night side. Solar panels may reflect particular wavelengths. Satellites or orbiting structures may cross the face of a star in unusual patterns. Many of these signals would be far below the reach of current telescopes for an Earth-like civilization at interstellar distance. A more extensive or longer-lived civilization might be easier to notice. Technosignature research, therefore, explores both current instruments and future possibilities. It asks what Earth would look like from afar, then considers what more visible technologies might resemble. The goal is not to predict every form another society could build. It is to identify effects that known physics allows and astronomical instruments can test. An atmosphere can become an archive of a planet's geology and biology. In rare circumstances, it may also preserve the quiet chemistry of invention. Breakthrough Listen searches a large portion of the radio and optical sky. The program begins in 2015 as a major expansion of modern SETI research. Its planned targets include 1 million nearby stars, the center and plane of the Milky Way, and a selection of nearby galaxies. Large radio observatories gather many frequencies at once. Optical instruments search for bright, brief pulses. The observations produce enormous amounts of data. Computers examine this data for structured signals. Most candidates come from human technology. A telescope may receive radar, satellite communication, navigation signals, or emissions from equipment nearby. Some interference enters through the side of the instrument, rather than arriving from the direction being observed. Researchers use repeated observations to identify it. A promising candidate should appear when the telescope points toward the target, and disappear when it points away. It should return during later observations. Independent observatories should be able to detect it. Its frequency may drift in a way consistent with an orbiting planet. Breakthrough Listen also releases substantial collections of data for wider analysis. Researchers can develop new methods and search observations again. Machine learning systems may help recognize interference and find patterns that older software overlooks. Human review remains important, especially when a candidate appears unusual. The program has examined signals that initially attract interest. Detailed follow-up has so far connected the strongest candidates to interference or has failed to detect them again. No confirmed technosignature has emerged. This outcome does not mean that the galaxy contains no technology. The search covers only selected directions, frequencies, times, and kinds of signals. A transmission can pass Earth while a telescope looks elsewhere. A narrow beam may never cross the solar system. Another civilization may communicate through a method not yet considered. For now, observatories continue collecting quiet pieces of the sky. Each observation makes the unexplored region slightly smaller. The absence of a confirmed signal is not the same as evidence of an empty galaxy. The possible search space is immense. There are billions of stars in the Milky Way. Around them may be even more planets and moons. A signal could arrive at almost any radio frequency. It could appear as visible light, infrared heat, atmospheric chemistry, or another physical effect. It might last for years. It might last for less than a second. It may repeat every few minutes, once each century, or not at all. Its source may transmit in every direction, or through a narrow beam aimed at one star. Earth may fall inside that beam only briefly. Time creates another difficulty. A civilization may exist millions of years before humanity develops radio astronomy. Its signals could pass through the solar system, while Earth contains only simple life. Another may arise millions of years in the future. Even if technological societies are common across cosmic history, they may rarely overlap closely in time. Distance adds further separation. A signal from a world 1,000 light-years away reveals that world as it existed 1,000 years ago. Any response from Earth requires another 1,000 years to arrive. A conversation across the galaxy would unfold more slowly than civilizations usually imagine conversation. The searches conducted so far sample only a small part of this wide space. They resemble examining a few cups of water from a vast ocean. Finding no fish inside those cups does not show that the entire ocean is still. The comparison is imperfect, but the lesson is useful. Silence can place limits on particular signals at particular strengths. It cannot yet describe every star, every frequency, and every moment. SETI becomes stronger as those limits are stated clearly. Science does not need to turn uncertainty into emptiness. It can measure what has been searched and leave the remaining sky open. The galaxy continues shining, while instruments listen to one narrow region at a time. The Fermi Paradox begins with a simple contrast. The Milky Way contains an enormous number of stars. Planets appear to be common. Many stars are older than the Sun, giving their worlds more time for life and technology to develop. Yet no confirmed evidence of another technological civilization has been found. No verified transmission has reached a radio telescope. No distant planet has revealed unmistakable engineering. No spacecraft from another star is known to have entered the solar system. This contrast is often summarized by a question associated with physicist Enrico Fermi. Where is everybody? The phrase Fermi Paradox can sound as though science has discovered a logical contradiction. It has not. The paradox depends on assumptions that remain uncertain. It assumes that life begins often enough. It assumes that intelligence and technology appear on some living worlds. It may also assume that technological societies remain active for long periods or spread beyond their original planets. None of these steps is yet measured beyond Earth. The apparent silence may have one explanation, several explanations, or no unusual explanation at all. Humanity may simply have searched too little of the sky. The question remains valuable because it connects many fields. Astronomy estimates how many stars and planets exist. Planetary science studies the conditions that preserve water and atmospheres. Biology investigates how life begins and evolves. Engineering determines which signals can be detected across great distances. The paradox, therefore, does not announce that something is missing. It asks whether current expectations are based on enough evidence. Perhaps living worlds are rare. Perhaps simple organisms are widespread. While technology is uncommon, perhaps civilizations are present but quiet, distant, brief, or difficult to recognize. Perhaps their light and signals are still traveling. The silent sky is not a completed answer. It is the calm boundary of what observation has reached so far. The Milky Way has existed far longer than the solar system. The universe is about 13.8 billion years old. The first generations of stars begin shining within its early history. Galaxies gradually grow as gas, stars, and smaller systems gather together. The Milky Way contains stars that formed billions of years before the Sun. Our solar system appears about 4.5 billion years ago. By then, many older stars have already completed long portions of their lives. Rocky planets may have formed around some of them. This creates the possibility that certain planetary systems receive an immense head start. A world that forms 2 billion years before Earth could, in principle, begin its biological history much earlier. If intelligence develops there at a pace similar to Earth's, technology might appear before the Sun even forms. This thought contributes to the Fermi Paradox. A civilization only 1 million years older than humanity would possess a span of time difficult to imagine. 1 million years is short compared with the age of the galaxy, yet it is thousands of times longer than the history of modern science. However, an old planet is not automatically a living one. The early galaxy contains fewer heavy elements than it does today. Carbon, oxygen, silicon, iron, and other materials accumulate through generations of stars. Some ancient environments may contain fewer ingredients for rocky worlds. Galactic conditions also change. Regions experience radiation, stellar explosions, gravitational encounters, and the movement of gas. A planet can be old but dry. It can lose its atmosphere. Its star can change in harmful ways. Its geology may never create a stable environment. Age provides opportunity, not certainty. The galaxy's long history leaves room for life to begin many times. It also leaves room for countless planets to remain quietly without biology. Between the oldest stars and the young solar system lies a great span of possibility, almost entirely unobserved. The size of the galaxy makes both contact and isolation possible. The Milky Way's disk stretches more than 100,000 light-years across. Light is the fastest messenger known. It travels nearly 300,000 kilometers each second. Even at that speed, crossing the galaxy requires tens of thousands of years. A radio message sent from the opposite side would begin its journey long before recorded human history and might still be traveling. Most stars are separated by several light-years. This appears small on a map of the galaxy, but it represents an immense physical distance. The nearest star beyond the Sun is more than 4 light-years away. A spacecraft moving at the speed of today's interplanetary probes would require thousands of years to approach such a distance. Communication is easier than physical travel, but it remains slow. A message to a civilization 100 light-years away arrives after 100 years. A reply requires another century. Neither society hears the other as it exists in the present. Each receives a record from the past. Distance can therefore turn a populated galaxy into a collection of separated islands. Signals weaken as they spread. Narrow beams may miss Earth. Civilizations may use communication systems that release very little energy into space. A planet can support technology without becoming visible across the Milky Way. The galaxy is also not observed all at once. Telescopes study selected directions for limited periods. A brief signal may cross Earth while the correct instrument is pointed somewhere else. A civilization may transmit for centuries, yet its message can still pass unnoticed during the long intervals between observations. The stars appear close together in the night sky because distance is flattened into a dark surface. In reality, each point of light is separated from the next by a deep and quiet volume. A habitable planet may remain lifeless. The word habitable describes an environment where known forms of life might survive. It does not mean that life has actually begun there. Earth contains liquid water, carbon chemistry, usable energy, and many essential elements. These conditions support a vast biosphere today. Scientists do not yet know which of them are sufficient for life to originate. A sterile laboratory can contain water, minerals, gases, and organic molecules. Those ingredients do not automatically organize themselves into cells. The origin of life requires chemistry to cross an unusual boundary. Simple molecules must form more complex networks. Some system must store information. Reactions must gather energy and maintain order. Structures must separate internal chemistry from the surrounding environment. Eventually, a system capable of reproduction and evolution must appear. Researchers explore several possible pathways. Some study reactions near hydrothermal environments. Others examine shallow pools where wet and dry cycles concentrate molecules. Ice, mineral surfaces, volcanic settings, and impacts may also assist different stages. No complete pathway has yet been demonstrated from ordinary planetary chemistry to the first evolving cells under known natural conditions. This uncertainty creates one of the largest gaps in estimates of life's abundance. If life begins readily whenever conditions are suitable, the galaxy may contain many microbial worlds. If the transition requires an extremely uncommon sequence, Earth may represent a rare outcome even among billions of temperate planets. The early appearance of life on Earth offers an encouraging clue, but it is difficult to interpret. Observers can only arise on a planet where life begins early enough for intelligence to evolve later. Earth's history may therefore be typical, fortunate, or somewhere between. A world can carry oceans beneath a gentle sky for billions of years, while its water remains chemically rich and completely still. Most of Earth's living history belongs to microorganisms. Life appears early in the geological record. Complex animals arrive much later. For billions of years, Earth is a microbial planet. Bacteria and archaea occupy oceans, sediments, rocks, and shallow water. They develop diverse ways to gather energy. Some use sunlight. Others use hydrogen, sulfur, iron, or methane. These organisms are small, but their planetary influence is immense. They alter minerals. They cycle carbon and nitrogen. Photosynthetic microbes gradually change the chemistry of the oceans and atmosphere. From a distant telescope, early Earth may not look like a world preparing to build cities or radio instruments. It may show only subtle atmospheric changes produced by microscopic life. This history suggests that the most common inhabited planet, if inhabited planets are common at all, could be microbial. Simple cells require less energy and fewer specialized structures than large organisms. They can occupy narrow environments and endure long periods of planetary change. Technological intelligence is not necessary for biological success. Microbes have survived every major transition in Earth's history. They remain present in nearly every environment today. The human body itself contains vast communities of them. If a spacecraft reaches an ocean moon and finds living cells, the discovery would transform biology. Yet those cells may never form larger creatures, regardless of how long their ocean persists. Evolution does not follow a planned staircase. It branches in response to local conditions. Traits that help organisms survive become common. Traits with no immediate advantage may disappear. Large bodies, nervous systems, hands, language, and technology are only some of the outcomes biology can explore. A living galaxy might therefore remain mostly quiet. Across countless worlds, life may consist of soft films on stone, drifting cells in water, and chemistry slowly remaking the air. Earth waits a very long time before oxygen becomes abundant. The earliest atmosphere contains little free molecular oxygen. Photosynthetic organisms eventually develop a way to use water as part of their energy-gathering chemistry. Oxygen is released as a byproduct. At first, much of this oxygen reacts with iron and other materials. It dissolves into oceans and is absorbed by rocks. The atmosphere does not change immediately. Around 2.4 billion years ago, oxygen begins accumulating more strongly during the Great Oxidation event. Even then, modern oxygen levels do not appear at once. Earth's atmosphere and oceans continue changing over immense periods. Oxygen rises, falls, and spreads unevenly through different environments. Large animals arrive only within the most recent portion of planetary history. Oxygen is important because it allows organisms to release substantial energy from food. That energy supports movement, complex tissues, active nervous systems, and larger bodies. Yet oxygen also brings chemical challenges. Early organisms, adapted to oxygen-poor environments, must retreat into protected habitats or develop ways to tolerate the new conditions. The rise of oxygen is not merely an atmospheric event. It is a long interaction between life, oceans, rocks, and the planet's interior. On another world, photosynthesis may never evolve. It may evolve but use chemistry that does not release oxygen. Oxygen may be produced while surface minerals absorb it for billions of years. A living planet could therefore appear lifeless to telescopes, searching only for an oxygen-rich atmosphere. The history of Earth warns against expecting a biosphere to display the same signature throughout its lifetime. For much of Earth's inhabited past, distant astronomers may struggle to recognize its life. A planet can be alive long before its atmosphere speaks clearly across space. Complex cells represent another uncertain step. Bacteria and archaea are built from cells without a nucleus. Their structures are efficient and remarkably adaptable. Animals, plants, fungi, and many microscopic organisms belong to another broad group called eukaryotes. Eukaryotic cells contain a nucleus and many specialized internal structures. One of the most important is the mitochondrion. Mitochondria help cells release usable energy. Evidence suggests that their ancestors begin as free-living bacteria. At some point in ancient history, one cell enters a close relationship with another. Instead of being digested or destroyed, the inner cell remains. Over generations, the two become increasingly dependent upon each other. This event, known as endosymbiosis, produces a new kind of cellular partnership. Mitochondria still carry a small amount of their own genetic material, preserving a trace of their independent origin. All known modern eukaryotes share a common ancestry. The surviving history of complex cells may therefore pass through a narrow evolutionary doorway. Scientists do not know how often similar partnerships occur on other planets. Perhaps cells naturally develop internal compartments and energy-producing partners when enough time is available. Perhaps the exact combination that leads to eukaryotic complexity is uncommon. Multicellular life evolves several times on Earth. Plants, animals, fungi, and different groups of algae each develop forms of cooperation among cells. Yet most multicellular organisms never create brains, tools, or technology. A forest is complex without producing radio. A coral reef contains intricate relationships without studying the stars. Biological complexity can grow in many directions. On another planet, large organisms may form living carpets, slow colonies, or floating structures unlike familiar animals. They may remain successful for hundreds of millions of years without developing anything that a radio telescope could hear. The path from chemistry to technology contains many branches, and only one known branch reaches the question of other worlds. Intelligence is useful in some environments, but evolution does not require it. Earth contains many forms of problem-solving. Birds remember locations and use tools. Octopuses explore objects and open containers. Dolphins communicate through complex sounds. Apes learn from social groups and adapt their behavior. These abilities develop independently in different branches of life. Intelligence is therefore not restricted to one evolutionary line. Yet human-style technology depends on a particular combination of traits. It benefits from precise manipulation, social learning, memory, communication, and access to suitable materials. It also depends on environmental opportunities. A highly intelligent aquatic species may find some technologies difficult. Fire does not remain available underwater. Smelting metals and building electrical systems may require a different path. A world covered entirely by deep ocean could support rich ecosystems and capable minds without creating radio telescopes. An intelligent species may also lack the motivation to transform its environment extensively. Evolution favors survival and reproduction, not astronomy. Curiosity can be useful, but it does not necessarily lead to mathematics, industry, or interstellar communication. On Earth, modern humans exist for a long period before producing detectable radio emissions. Scientific institutions, written knowledge, manufacturing, and global cooperation developed through a complex cultural history. Small differences could redirect that history. A stable species may live successfully with simple tools. Another may develop advanced understanding but use little energy. A civilization may study its sky through methods that release no strong signal. Technology is one possible expression of intelligence, not its guaranteed destination. The galaxy could contain minds that never become visible to current instruments. Some may look inward, building rich cultures beneath oceans or thick clouds. Their worlds would not be empty. They would simply remain beyond the kinds of evidence Earth currently knows how to collect. A technological civilization may be detectable for only a small portion of its existence. Earth has produced strong artificial radio signals for little more than a century. That period is extremely brief compared with the age of the planet. It is even briefer compared with the lifetime of the Milky Way. Technology also changes quickly. Early radio and television systems release substantial energy in many directions. Modern communications often use lower power, digital encoding, cables, fiber optics, and focused beams. Signals can become more efficient and less visible from interstellar space. Powerful radar remains more noticeable, but radar beams cover limited directions. A distant observer must be located inside the beam when it passes. A civilization could therefore move through a radio-bright phase and become quieter without disappearing. Its communication may shift to lasers, neutrinos, tightly directed radio, or methods not yet developed on Earth. Its energy systems may also become difficult to detect. Efficient technology can reduce waste. Populations may stabilize. A society may choose to preserve its planetary environment rather than build structures throughout its star system. The duration of detectability is one of the least understood terms in the Drake equation. If societies remain easily visible for millions of years, many generations can overlap across the galaxy. If their obvious signatures last only a few centuries, two neighboring societies may miss each other in time. One may finish its bright technological period before the other begins. The first century of Earth's radio history has expanded only a little more than 100 light-years in radius. Even within that region, ordinary leakage may be too weak for distant instruments to recognize. Earth has only recently become a possible point of technological light. The surrounding galaxy may contain other points whose brief glow has already softened into quiet efficiency. Interstellar expansion is possible in models, but it is not inevitable in behavior. The Fermi Paradox often considers a civilization that sends settlements from one star to another. Each new settlement eventually sends out more travelers. Over enough time, the process spreads through a large part of the galaxy. Even with spacecraft moving far below the speed of light, some models complete this expansion in much less time than the age of the Milky Way. This leads to another form of Fermi's question. If any civilization begins spreading long ago, why is its activity not visible here? The reasoning is useful, but it contains assumptions. It assumes that distant settlements continue expanding. It assumes that the process remains worthwhile for thousands or millions of years. It also assumes that inhabited systems become recognizable. A civilization may send scientific probes rather than permanent settlements. It may explore nearby stars and then stop. Each distant community may make independent choices. Expansion can occur slowly, unevenly, or in waves. Stars themselves move through the galaxy. Over millions of years, different systems pass relatively close to one another. Travelers may wait for favorable encounters instead of crossing the widest gaps. Other regions may be difficult to reach or offer little value. A society with advanced manufacturing may obtain all needed resources from its own asteroids, moons, and star. Moving living populations between stars may provide few practical benefits. Even if expansion occurs, visible traces may not last forever. Machines can fail, structures can be dismantled, orbits change, geological activity covers surfaces. A quiet settlement may resemble a natural planet from far away. The galaxy need not be completely empty for the solar system to remain unvisited. Interstellar movement may form scattered threads rather than one continuous wave. Between those threads, many planetary systems could continue their ordinary orbits without ever receiving a traveler. A civilization may choose depth rather than distance. Human imagination often connects technological growth with increasing energy use and physical expansion. This pattern reflects part of Earth's recent history. It may not describe every possible future. Improved technology can sometimes accomplish more with less material and energy. Computers become smaller. Communication carries more information through narrower channels. Recycling reduces the need for new resources. Virtual environments allow experiences without long physical journeys. A mature civilization might concentrate on knowledge, art, biology, computation, or carefully managed habitats. Its population may remain stable. Its machines may operate near a home planet or within one star system. Such a society could survive for a long time without constructing a galaxy-wide presence. A single planetary system contains enormous resources. Asteroids hold metals and minerals. Comets contain water and carbon compounds. A star provides energy for billions of years. Artificial habitats could offer additional living space without requiring travel to another sun. This does not prove that advanced societies remain local. Some may explore widely, others may divide into many different communities, each following a separate path. The main lesson is that technological capability does not dictate one universal choice. The absence of large visible structures may reflect restraint, efficiency, or simple contentment rather than absence. A civilization can be advanced without becoming astronomically bright. From Earth, a quiet system may look like an ordinary star surrounded by ordinary planets. Its greatest achievements might occur in patterns too small, too focused, or too subtle to be seen across light years. A galaxy can contain intelligence while keeping most of its starlight unchanged. Civilizations must overlap in both space and time to communicate. Imagine two inhabited planets separated by 500 light-years. The first develops radio technology and remains detectable for 300 years. Its signals expand outward as a growing shell. The second develops similar technology 1,000 years later. By the time its instruments are ready, the first civilization's strongest signals may have already passed. A reply cannot begin because the listening periods do not overlap. The worlds share the same galaxy, yet they never become aware of each other. This timing problem becomes larger across cosmic history. Stars form at different dates, planets stabilize at different rates. Life may begin quickly on one world and slowly on another. Evolution can pause during changes in climate, atmosphere, or geology. Technology may appear, fade, return, or transform. A civilization that lasts 10,000 years seems ancient by human standards. Against a galactic history measured in billions of years, it occupies a very narrow interval. For many societies to communicate, their detectable intervals must cross. Distance then adds another delay. Each civilization sees the other's past. A signal arriving today may come from technology that changed centuries ago. The sender cannot know Earth's present condition. Deliberate communication may therefore require patience across generations. Some societies might build beacons designed to transmit for thousands of years. Others may not consider such projects valuable. Natural astronomical events are often easier to detect because they continue for immense periods or release extraordinary energy. Technology may be quieter and shorter. The Fermi Paradox sometimes imagines all civilizations existing together in one shared galactic present. Relativity offers no single present across such distances. There are only signals moving between stars, each carrying an earlier image of its source. The galaxy may be filled with histories that pass one another without meeting. The Great Filter is a name for one or more difficult steps between lifeless matter and visible civilization. The concept does not identify which step is difficult. The filter could appear near the beginning. Perhaps the origin of life is extraordinarily rare. Many planets may contain water and organic chemistry, while never forming evolving cells. The filter could come later. Simple life may arise often, while complex cells seldom appear. Multicellular organisms may remain uncommon. Intelligence capable of abstract language may develop on only a small fraction of living worlds. The difficult step might involve culture and technology. Intelligent organisms may rarely create scientific traditions or instruments. Technological societies may remain detectable for only short intervals. There could also be several moderate filters, rather than one nearly impossible event. Each step reduces the number of worlds that continue toward the next. By the end, visible civilizations become sparse, even if microbial life is widespread. Earth cannot yet reveal where these filters lie. Life begins early here, which may suggest that the first step is not extremely difficult. Yet one inhabited planet provides too little evidence for a reliable probability. Complex life takes much longer. Technological civilization appears only near the end of Earth's current history. These timings are clues, but they are shaped by local conditions and by the fact that observers necessarily find themselves on a world where every required step has already occurred. Discoveries elsewhere would change the picture. Independent microbial life on Mars or an ocean moon would suggest that biology can begin more than once within one planetary system. Complex life on a nearby exoplanet would show that later transitions are not unique to Earth. A technosignature would reveal that at least one other world has crossed the entire sequence. The Great Filter is therefore not a prediction of what must happen. It is a quiet way to organize the unknown steps between chemistry, cells, minds, and stars. Silence becomes meaningful only when the search is measured carefully. A telescope that finds no signals still produces knowledge. It can show that no transmitter above a certain power was present within the observed frequency range during that particular time. An infrared survey can limit the number of galaxies dominated by enormous amounts of waste heat. Atmospheric observations can rule out certain gases at detectable concentrations. Each result removes a small region from the space of possibilities. The wording matters. No signal detected does not mean no civilization exists. It means that a particular kind of evidence was not found under particular observing conditions. As telescopes improve, those conditions expand, more stars are examined, wider frequency ranges are recorded, computers search for weaker and more complex patterns. Future observatories may study the atmospheres of nearby rocky planets. They may search for combinations of biological gases, manufactured compounds, surface reflections, or unusual night-side light. Solar system missions may examine ancient ice, lunar soil, asteroids, and planetary surfaces for records preserved across long periods. No single method can answer every version of the question. Microbial life may require samples and microscopes. Atmospheric life may reveal chemistry. Technology may appear through radio, light, heat, structures, or artifacts. The search gradually becomes a network of complementary observations. The apparent silence grows more informative as the listening becomes deeper. For now, the Milky Way offers neither confirmation nor final emptiness. It offers stars of many ages, planets of many kinds, and a question that remains open beneath their combined light. The universe has not answered that humanity is alone. It has simply allowed the search to begin. Alien life may be unfamiliar in shape while remaining familiar in chemistry. Every known organism on Earth is built mainly from carbon-rich molecules and liquid water. Cells use membranes to separate their inner chemistry from the environment. They store inherited information and gather energy to maintain themselves. Life elsewhere does not have to copy these exact details. Its genetic material may differ from DNA. Its cells may use unfamiliar pigments. Its metabolism may depend on chemicals rarely used by Earth organisms. Yet the laws of physics and chemistry remain the same everywhere. Carbon atoms behave around another star as they behave in the solar system. Water freezes, melts, dissolves substances, and carries heat according to the same molecular rules. Energy must still be gathered, stored, and released. This creates a balance between possibility and constraint. Life may explore countless combinations, but not every combination works equally well. Certain elements form more stable structures. Certain liquids transport molecules more effectively. Some energy sources remain available for longer periods. Astrobiology often begins with life as it is known because it provides the only complete example available. This does not mean that Earth chemistry is assumed to be universal. It means that familiar biology offers a practical place to start. A telescope can search for water because water leaves measurable patterns in light. A spacecraft can examine organic molecules because their structures can be identified. An instrument can look for repeating chemical imbalances because life on Earth creates them. Truly unusual life may require new methods. It may not release oxygen. It may not use sunlight. It may leave patterns that have not yet been recognized as biological. Even so, an organism formed beneath another sky must still build order from matter. Alien life may be wonderfully different, while quietly following the same natural laws. Carbon is unusually well suited for building complex living chemistry. A carbon atom can form 4 strong chemical bonds. This allows it to connect with several other atoms at once. Carbon can create long chains, branching structures, flat rings, and intricate 3-dimensional shapes. It bonds readily with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and other carbon atoms. These combinations form an enormous range of molecules. Proteins, sugars, fats, genetic material, pigments, and cell membranes all depend on carbon frameworks. Small changes in the arrangement of atoms can produce molecules with entirely different properties. Carbon bonds are stable enough to preserve structure, yet flexible enough to participate in reactions. This balance matters. A molecule that falls apart too easily cannot store information or build a lasting cell. A molecule that never reacts cannot support metabolism or adaptation. Carbon occupies a useful middle ground. It is also common throughout the universe. Stars produce carbon through nuclear reactions. Stellar winds and explosions spread it into space. Astronomers detect carbon-bearing molecules inside interstellar clouds, comets, meteorites, planetary atmospheres, and disks around young stars. The basic element therefore reaches planetary systems before life begins. Carbon chemistry can become complex without biology. This makes the discovery of organic molecules important but not decisive. A meteorite containing amino acids does not necessarily contain evidence of an organism. It demonstrates that nature can assemble part of biology's molecular vocabulary through ordinary chemistry. On a suitable world, those molecules may gather inside oceans, warm pools, ice, rock pores, or atmospheric droplets. Whether they become alive depends on further steps that remain incompletely understood. Other elements may contribute to unfamiliar life, but carbon remains a strong candidate wherever complex chemistry develops. Across the galaxy, one small atom offers nature an extraordinary number of ways to build. Liquid water provides a gentle meeting place for chemistry. Water is a simple molecule made from 2 hydrogen atoms and 1 oxygen atom. Its shape gives it an uneven electrical charge. One region is slightly negative, while another is slightly positive. This allows water molecules to attract ions and many other polar molecules. As a result, water is an effective solvent. Substances dissolve and move through it. Molecules encounter one another. Chemical reactions can unfold throughout a liquid environment rather than only where solid surfaces touch. Inside Earth's cells, water carries nutrients, salts, proteins, and waste products. It supports reactions and helps large molecules fold into useful shapes. Water also remains liquid across a useful range of temperatures under appropriate pressure. It absorbs a large amount of heat before changing temperature quickly. Oceans therefore soften daily and seasonal changes, helping planetary climates remain more stable. Frozen water has another unusual quality. Ordinary ice is less dense than liquid water, so it floats. A layer of ice can cover a lake while liquid remains below. The surface then acts as insulation, protecting the deeper environment from colder air. On ocean moons, thick ice may similarly shield liquid water from space. Water is not perfect for every chemical process. Some molecules break apart within it. Other substances barely dissolve. Biology manages these limits, using membranes, enzymes, and carefully controlled compartments. Alternative liquids might support different kinds of chemistry. Still, water combines abundance, stability, heat storage, and strong dissolving power in one material. Hydrogen and oxygen are also common cosmic elements. This is why the search for water remains central to astrobiology. Water does not prove that life is present. It creates a place where molecules can meet, drift, exchange energy, and perhaps begin organizing themselves. In a quiet ocean, chemistry gains both movement and time. Liquid ammonia could support chemistry in colder environments. Ammonia contains nitrogen and hydrogen. Under Earth-like pressure, it becomes liquid at temperatures far below the freezing point of water. This makes it interesting as a possible solvent on cold planets and moons. Ammonia is a polar molecule, so it can dissolve various substances. Some chemical reactions that occur in water may also occur in liquid ammonia, although their rates and products would differ. A world with ammonia-rich lakes might support molecular structures, unlike ordinary Earth biology. Its environment would be cold. Reactions generally proceed more slowly at low temperatures. Metabolism might therefore unfold at a gentle pace. An organism could require long periods to grow, reproduce, or respond to environmental change. Ammonia also presents challenges. It remains liquid across a narrower temperature range than water under many conditions. It is chemically reactive and can affect molecules that Earth organisms depend upon. A thicker atmosphere or higher pressure could help stabilize it as a liquid. Mixtures of ammonia and water can also remain fluid at lower temperatures than pure water. Such mixtures may exist inside some icy moons. Ammonia has been considered as an antifreeze within subsurface oceans. By lowering the freezing temperature, it can help liquid persist farther from a star. No ammonia-based organism is known. The idea remains a scientific exploration of what chemistry might permit, rather than evidence for a second form of biology. A life detection instrument designed only for Earth-like water chemistry might overlook something adapted to an ammonia-rich environment. Researchers therefore consider how unfamiliar solvents would change membranes, metabolism, and molecular information. On a cold world beneath a faint sun, life might not hurry. Its chemistry could move slowly through dark liquid, completing one quiet reaction after another. Methane and ethane create lakes where water is frozen as hard as stone. Titan provides the clearest known example. Its surface is so cold that methane and ethane can flow as liquids. They form clouds, rain, rivers, lakes, and broad northern seas. These hydrocarbons are very different from water. They are non-polar solvents. Molecules that dissolve easily in water may not dissolve in liquid methane. Any biology using such a liquid would require a different internal chemistry. Ordinary Earth cell membranes would not work in the same way. Researchers have explored theoretical structures that might form stable boundaries inside methane. Such ideas remain models rather than discovered organisms. Energy presents another question. Sunlight at Titan is faint. Its atmosphere filters and scatters much of what arrives. Chemical reactions may provide energy, but the low temperature makes many reactions slow. A methane-based ecosystem might therefore operate at a pace far below familiar biology. Growth could take years or centuries. Environmental changes might be measured through long seasons rather than days. Titan's atmosphere continuously creates organic molecules. They settle across its surface and enter the lakes. This provides abundant carbon chemistry, although abundance alone does not create life. Liquid methane may be too cold or chemically limited for biological complexity. It may also permit pathways that have never occurred on Earth. The only way to know is through observation. Future missions can examine lake compositions, atmospheric chemistry, and surface materials. They can search for patterns that ordinary chemistry has difficulty producing. Such patterns might include unexpected molecular distributions or energy imbalances. A methane organism would not resemble a fish beneath clear water. Its molecular foundation would be different from the beginning. Under Titan's amber haze, even the meaning of an ocean changes. Silicon can build complex structures, but it does not imitate carbon easily. Silicon sits below carbon in the periodic table. Like carbon, it can form 4 chemical bonds. This similarity has encouraged speculation about silicon-based life. Silicon is also abundant in rocky planets. It combines with oxygen to form silicate minerals, which make up much of Earth's crust and mantle. Sand, clay, and many stones contain silicon, yet abundance does not automatically make it suitable for biology. Carbon bonds readily with itself, producing stable chains and rings. Silicon can also bond with itself, but these structures are often less stable under conditions where water is liquid. Silicon strongly prefers bonding with oxygen. The resulting compounds are commonly solid minerals. Carbon dioxide is a gas under familiar surface conditions and can move easily through an atmosphere. Silicon dioxide usually forms a solid. This difference could make a silicon metabolism less flexible. A living system must gather raw materials and remove waste. A solid mineral byproduct is more difficult to transport than a gas or dissolved molecule. Silicon chemistry may become more varied in environments unlike Earth. High temperatures, low oxygen, or unusual solvents could allow compounds that do not remain stable in water and air. Silicon might also support life as one important ingredient rather than replacing carbon entirely. Earth organisms already use it in limited ways. Diatoms build delicate shells from silica. Some plants incorporate silicon into their tissues. No known organism uses long silicon chains as the main framework of its metabolism or genetic system. The concept is therefore possible in imagination, but restricted by chemistry. Alien life may teach science that other elements can support information and metabolism. It may instead reveal that carbon's flexibility makes it common wherever biology appears. Across rocky planets, silicon builds mountains easily. Whether it can build a cell remains a quieter question. Alien life could use molecules with the opposite-handedness from life on Earth. Many biological molecules come in forms that resemble mirror images. A human left hand and right hand have the same parts, but they cannot be perfectly placed on top of each other. Certain molecules behave in a similar way. This property is called chirality. Amino acids can exist in left-handed and right-handed forms. Sugars can also have opposite arrangements. Life on Earth shows a strong preference. Proteins are built almost entirely from left-handed amino acids. Genetic systems use sugars of the opposite general-handedness. Non-living chemistry often produces mixtures containing both forms. How early biology selects one orientation remains an open question. A small initial imbalance may become amplified as molecules reproduce or assist the formation of similar molecules. Mineral surfaces, light, or chance events may influence the first preference. Life elsewhere might make the opposite choice. Its proteins could use right-handed amino acids. Its genetic material could be based on mirror image sugars. Such organisms might appear chemically familiar while remaining biologically separate. Earth enzymes are shaped to interact with molecules of particular handedness. A mirror molecule may not fit correctly, much as the wrong key fails to enter a lock. This could make two biospheres unable to digest or infect each other, even if both depend on carbon and water. Chirality may also become a biosignature. If a sample contains a strong preference for one molecular orientation, the imbalance could suggest a process capable of selecting and maintaining it. Non-biological mechanisms can create smaller imbalances, so context would remain essential. A future microscope may find cells that look simple and familiar. Their chemistry may reveal that their history began independently. A mirror can preserve the same pattern while quietly reversing every turn. Evolution by natural selection may operate wherever life reproduces imperfectly. Earth's organisms contain inherited information. When they reproduce, most information is copied accurately. Small changes sometimes occur. Environmental conditions then influence which variations leave more descendants. This process is natural selection. It does not require foresight or a planned destination. It requires replication, variation, and differences in reproductive success. Any alien system with these properties could evolve. Its information carrier does not have to be DNA. It could use another molecule or a network of interacting chemical structures. Once inheritance and variation exist, populations can gradually become better suited to local conditions. On a dim planet, pigments may become more efficient at gathering available light. In a moving ocean, shapes that reduce resistance may spread. In a changing climate, flexible metabolism may provide an advantage. Evolution does not always create greater complexity. Simple organisms can remain highly successful. Traits can disappear when they cost more energy than they provide. Some species become specialized for stable environments, while others remain adaptable. Chance also matters. Mutations occur without regard to future need. Geological events alter habitats. Populations become separated. Entire evolutionary paths can depend on small events in earlier generations. Alien life would therefore be shaped by both universal principles and local history. Natural selection may be common, but its results would not be predictable in detail. Two similar planets might begin with comparable chemistry and eventually develop very different biospheres. One may remain microbial, another may fill its oceans with large drifting colonies. A third may lose life after its environment changes. Evolution is a quiet conversation between organisms and the places that contain them. Across another world, that conversation could continue for billions of years without repeating Earth's exact sentences. Similar environmental problems can lead evolution towards similar solutions. This process is called convergent evolution. Birds, bats, and insects develop wings independently. Their wings differ in structure, yet all create surfaces that push against air and generate lift. Dolphins, sharks, and extinct marine reptiles develop streamlined bodies. Their evolutionary histories are separate, but moving efficiently through water favors related shapes. Eyes also evolve in several forms. Camera-like eyes appear in vertebrates and cephalopods such as octopuses. The details differ, but both use a lens to focus light onto sensitive tissue. Convergence suggests that some biological designs may appear more than once because physics limits the number of effective solutions. Water rewards smooth shapes. Gravity favors structures that support weight. Light can be focused with lenses or reflected with mirrors. Alien organisms living under similar conditions might therefore show familiar patterns. A creature moving rapidly through an ocean may be tapered at both ends. A large land organism may use multiple supports beneath its body. A photosynthetic organism may spread broad surfaces toward the sky. This does not mean that alien animals would resemble specific Earth species. Their tissues, senses, colors, and internal structures could be entirely different. Local evolution may find alternatives that Earth never explores. Convergence is also not guaranteed. A useful trait can arise only if earlier biology provides a path toward it. Historical accidents shape which structures are available for modification. A world can solve a familiar problem in an unfamiliar way. Still, natural laws gently guide the possibilities. If life fills enough planets, some forms may appear almost recognizable from a distance. The universe may repeat a few quiet shapes, while changing every smaller detail. Plants beneath another star may not be green. Earth's plants look green because chlorophyll absorbs red and blue light more strongly while reflecting much of the green portion. Photosynthesis uses captured light to power chemical reactions. Other organisms use different pigments. Some bacteria absorb wavelengths that chlorophyll does not. Algae living at different water depths carry pigments suited to the light that reaches them. The color of alien photosynthesis would depend partly on the star. A red dwarf releases more of its energy at red and infrared wavelengths than the Sun. A planet around such a star receives a different spectrum at its surface. Organisms may develop pigments that gather those wavelengths efficiently. Atmospheric gases would also filter the light. Clouds, haze, and ocean water could remove some colors while allowing others to pass. A biosphere might therefore appear dark purple, orange, red, brown, or almost black. Black surfaces absorb a broad range of visible light, although excessive heating could create other challenges. The brightest available wavelengths are not always the only ones biology uses. Atmospheric chemistry and protection from energetic radiation may influence where photosynthesis occurs. Some organisms may live beneath water, ice, rock, or translucent mineral layers. Photosynthesis may not evolve at all. A biosphere powered by chemical energy could remain beneath the surface. disconnected from starlight. It might create no broad color signature visible from orbit. Astronomers consider surface reflectance as one possible biosignature. Earth vegetation produces a sharp change in reflectivity near infrared wavelengths, sometimes called the vegetation red edge. Alien pigments might create a different spectral edge. A distant world could carry living colors that no human language has named. Its surface would quietly transform starlight into chemistry, one photon at a time. Gravity would shape the bodies and movements of alien organisms. A planet more massive than Earth may have stronger surface gravity, although mass, radius, and density all influence the exact result. In strong gravity, lifting a body requires more energy. Tall structures need greater support. Limbs must resist larger forces. Falling becomes faster and more costly. Land organisms may therefore remain low to the ground. They may have broad bases, thick support tissues, or many limbs that distribute weight. Plants or plant-like organisms might grow outward instead of upward. A lower gravity world offers different possibilities. Tall, slender structures require less support. Animals may leap farther. Floating or gliding could become easier if the atmosphere is sufficiently dense. Low gravity does not remove the need for structure. Wind, movement, and internal fluid pressure still place stress on tissues. Body size would also depend on food, oxygen, or another energy-carrying gas, temperature, and evolutionary history. Gravity affects oceans and atmospheres too. A small world may struggle to hold light gases over billions of years. A massive planet can retain a deeper atmosphere, creating high pressure near the surface. Organisms within water feel buoyancy, reducing the direct importance of weight. Ocean life may therefore grow large even under stronger planetary gravity. A deep atmosphere can create a similar effect for floating organisms. No simple rule determines that high gravity makes all life small, or low gravity makes it large. Physics creates tendencies, while biology works within them. The shape of a tree, wing, shell, or skeleton records a long negotiation with downward pull. On another planet, every living structure would quietly reveal the strength of the world beneath it. A thick atmosphere could make the sky an ocean for living things. Atmospheric density changes the way objects move. Dense air provides more lift for a wing. It also creates greater resistance. An organism may remain aloft with a broader body and slower movement. On Titan, the atmosphere near the surface is denser than Earth's, while gravity is much weaker. These conditions would make mechanical flight easier, although Titan's cold chemistry presents other limits for known life. On a warmer planet with dense air, aerial ecosystems could become extensive. Small organisms might drift like plankton in an ocean. Larger creatures could glide for long periods, gathering energy or feeding on suspended material. Plants or microbial colonies might release floating structures that remain high in the atmosphere. Venus has inspired studies of possible microbial life inside cloud droplets, where temperature and pressure are milder than at the surface. The environment remains strongly acidic and extremely dry, creating major challenges. Still, the idea shows that a planet's habitable region need not rest on the ground. Cloud layers can contain water, chemicals, sunlight, and moving air. An organism living permanently in the atmosphere must avoid settling into unsuitable depths. It may regulate buoyancy using gas-filled chambers, changing density, or upward air currents. Its life cycle could follow global winds. Dense atmospheres also soften temperature differences by moving heat. They can protect the surface from some radiation and allow sound to travel differently. Aerial life would experience a world without firm boundaries. Habitats would move, mix, rise, and descend. Instead of roots in soil, organisms may depend on pressure, wind, and chemistry to remain within a narrow layer. Around a distant world, a living cloud could circle the planet many times before returning to the same region of sunlight. Tidally locked planets may contain a permanent sunset around their middle. A planet orbiting close to a small star can become tidally locked. Its rotation matches its orbital period. One hemisphere continually faces the star, while the other remains turned away. The bright side experiences constant daylight. The dark side receives no direct starlight. Between them lies a boundary called the terminator. From the surface, the star may appear fixed near the horizon in this region. The landscape would rest beneath an enduring dawn or sunset. Early models sometimes imagine the day side becoming too warm and the night side freezing completely. Atmospheres and oceans can transport energy. Winds move warm air toward the dark hemisphere. Cooler material returns toward the illuminated side. Ocean currents can perform a similar exchange. With suitable pressure and composition, broad regions may maintain moderate temperatures. Clouds could gather above the point directly beneath the star. By reflecting light, they may prevent excessive warming. Life on such a planet would adapt to stable directions. Photosynthetic organisms may always orient toward the same part of the sky. Migrating species could move toward or away from the terminator as climate changes. The night side might support organisms powered by chemical energy or nutrients carried from brighter regions. Weather patterns could form long-lasting structures because the planet's lighting never follows a daily cycle. Winds may flow continuously between the hemispheres. Storms may gather in preferred locations. Biology would not measure time through sunrise and sunset. Rhythms might follow the planet's orbit, stellar activity, seasons caused by orbital shape, or internal cycles. A tidally locked world is not half alive and half frozen by necessity. It may contain a ring of mild landscapes beneath a star that never rises and never sets. A living planet may hide almost its entire biosphere beneath the surface. Earth's visible forests and oceans make life appear closely connected to sunlight. Yet organisms also live deep underground. Microbes occupy fractures in rock, pores between mineral grains, and sediments beneath the seafloor. They obtain energy from chemical reactions involving hydrogen, sulfur, iron, methane, and other substances. Their metabolism can be extremely slow. Some communities survive with very limited energy, repairing themselves and dividing only rarely. Subsurface environments provide stability. Rock protects organisms from ultraviolet radiation, surface temperature changes, impacts, and dry conditions. Water can remain trapped underground after the surface becomes cold or barren. Mars may once have supported rivers and lakes. If life begins during that wetter period, later organisms might retreat below ground as the atmosphere thins. Icy moons offer an even larger hidden environment. Europa and Enceladus place their oceans beneath kilometers of ice. Any ecosystem there would remain invisible in ordinary images. A planet orbiting a red dwarf might similarly preserve life beneath water or rock, protected from stellar flares. This creates a challenge for remote astronomy. A deep biosphere may exchange very little material with the atmosphere. It may produce no visible surface color and no detectable gas. A world could contain living cells across a vast underground volume while appearing quiet through a telescope. Direct exploration may be required. Landers can drill, collect plume particles, examine freshly exposed ice, or search minerals for patterns created by metabolism. The first alien biosphere may not be found beneath a blue sky. It may rest in darkness, supported by the slow chemistry of water and stone. Life itself may be easier to recognize as a pattern than as a particular molecule. Earth biology uses DNA, proteins, cell membranes, and familiar metabolic compounds. A search restricted to those exact materials could miss an independent form of life. Agnostic life detection attempts to look for broader characteristics. Living systems organize matter. They maintain chemical differences from their surroundings. They build complex structures and use energy to remain far from equilibrium. They may favor certain molecular sizes, arrangements, or handedness. They may create repeating structures that carry information. None of these features alone proves life. Crystals form ordered shapes. Fire consumes energy and spreads. Non-living chemistry creates complex organic molecules. The strongest evidence comes from several patterns appearing together. A sample may contain compartments resembling cells. Molecules may show a consistent handedness. Chemical abundances may be difficult to explain through geology alone. Structures may reproduce or change in response to their environment. Future instruments are being designed to examine many scales, from individual molecules to microscopic particles. Some may analyze motion. Others may sequence familiar genetic material, while also searching for unexpected polymers and chemical distributions. This flexible approach matters, because the first independent life may not fit Earth's categories. It may blur familiar boundaries between organism, colony, mineral surface, and chemical network. Science will need patience. A strange pattern must be tested against contamination, instrument effects, and unknown non-biological processes. Confirmation may require several missions and laboratories. The goal is not simply to find something that looks like a cell. It is to recognize matter that continually gathers energy, preserves information, and makes more organized matter like itself. Alien life may first appear not as a creature, but as a quiet pattern that nature keeps repeating. The search for life is moving from broad possibility toward closer examination. The first discoveries of exoplanets reveal that worlds are common. Solar system missions show that water, organic molecules, and chemical energy exist in many places. The next step is more demanding. Scientists must learn which worlds are genuinely habitable. They must identify places where life could leave a measurable trace. Instruments must then separate that trace from ordinary chemistry, geology, and contamination. This work unfolds at several scales. Spacecraft can approach nearby planets and moons. They can measure magnetic fields, map ice, analyze gases, drill into rock, and collect individual grains. Telescopes study planets that remain many light years away. They examine tiny changes in starlight and search atmospheres for gases. Laboratories on Earth recreate unfamiliar environments. They place molecules under cold temperatures, high pressures, strong radiation, and unusual chemical conditions. Computer models connect these observations. A model may describe how an ocean circulates beneath an icy shell. Another may calculate how gases move through a distant atmosphere. Others explore which biological signatures survive long enough to be detected. No single observation can carry the entire search. A telescope may identify methane, but not reveal its source. A rover may find organic molecules without showing whether life produced them. A spacecraft may discover a warm ocean that remains entirely uninhabited. The answer grows from several kinds of evidence meeting together. This makes astrobiology less like opening one hidden door and more like assembling a quiet mosaic. Each mission contributes one piece. Each laboratory result clarifies its shape. Each new telescope adds detail to a picture that has only begun to form. Europa Clipper is traveling toward one of the solar system's most promising ocean worlds. The spacecraft leaves Earth in October 20. Its long route uses the gravity of other planets to adjust its speed and direction. It is expected to reach Jupiter in 2030. Europa Clipper will not enter orbit around Europa itself. Instead, it will orbit Jupiter and repeatedly pass close to the Moon. This arrangement protects the spacecraft from spending all its time inside the strongest regions of Jupiter's radiation. During dozens of close flybys, its instruments will study Europa from different distances and angles. Radar will send signals into the icy shell. The returning echoes may reveal layers, fractures, and regions where liquid water lies closer to the surface. Cameras and spectrometers will map the Moon's colors and chemical composition. They will examine dark lines, bright planes, and material that may have risen from below. A magnetometer will study the ocean indirectly through its electrical response to Jupiter's magnetic field. Other instruments will measure gravity, temperature, dust, gas, and charged particles surrounding the Moon. Europa Clipper is not designed to announce that life has been found. Its central question is whether Europa contains environments that could support life. Scientists want to understand the thickness of the ice, the depth and salinity of the ocean, the chemistry of the surface, and the movement of material between them. A place where ocean water reaches the upper ice would be especially interesting. Fresh material may preserve information from an environment hidden far below. The mission turns Europa from a pale point beside Jupiter into a complex planetary system of ice, water, salt, energy, and motion. With each flyby, the unseen ocean will become slightly less distant. JUICE is traveling toward a wider family of ocean-bearing moons. The European Space Agency launches the Jupiter Icy Moons Explorer in April 2023. Its shortened name, JUICE, reflects its destination and purpose. The spacecraft is expected to arrive in the Jupiter system in 20. It will study the giant planet and three of its largest moons, Europa, Callisto, and Ganymede. All three are thought to contain water beneath their surfaces. JUICE will observe Europa during a smaller number of close encounters. Europa Clipper will provide the more concentrated investigation of that moon. JUICE will give special attention to Ganymede. After years of observations around Jupiter, the spacecraft is planned to enter orbit around Ganymede. It would become the first spacecraft to orbit a moon belonging to a planet other than Earth. Ganymede is a world of unusual layers. It has an icy crust, a suspected deep ocean, a rocky interior, and an internally generated magnetic field. Some models suggest that several layers of liquid water may be separated by high-pressure forms of ice. JUICE will map the surface and study the moon's gravity. Radar will examine structures beneath the ice. Magnetic measurements will help researchers understand the ocean and interior. The spacecraft will also observe how Ganymede interacts with Jupiter's enormous magnetic environment. Callisto offers a different history. Its heavily cratered surface is ancient and comparatively quiet. A buried ocean may remain beneath a crust that has changed little for billions of years. By comparing these moons, researchers can study how size, internal heat, ice thickness, and distance from Jupiter shape possible habitats. They formed within one planetary system, yet each followed a different path. Juice will read those paths together, like three old chapters written in water and ice. Dragonfly will move across Titan by flying from one landscape to another. Titan's dense atmosphere and low gravity make powered flight unusually practical. NASA's Dragonfly mission is being built as a large rotorcraft. It resembles a drone with several pairs of rotors, although it is designed for an environment far colder and more distant than Earth. The mission is scheduled to launch no earlier than 2028 and reach Titan during the following decade. After landing, Dragonfly will not remain in one place. It will make repeated flights across the surface, traveling to sites with different geology and chemistry. A journey through the air can cover far more ground than a traditional rover moving slowly across rough terrain. Titan offers an extraordinary natural laboratory. Organic compounds form high in its atmosphere and settle toward the ground. Methane rain shapes river channels and lakes. Water ice forms much of the solid surface. Impact craters may bring these materials together. When a large object strikes Titan, the heat can melt water ice temporarily. Liquid water may then mix with complex organic material from the atmosphere. Dragonfly will examine areas where such chemistry may have occurred. Its instruments will analyze surface samples, measure atmospheric conditions, study local weather, and examine the physical character of the landscape. The mission is not expected to find forests, animals, or open water. It is searching for the chemical steps that come before life, and for signs that Titan once created environments where more advanced chemistry could develop. Titan resembles the early Earth in some ingredients while differing greatly in temperature and liquid environment. Studying it may reveal whether the pathways toward biology are common, narrow, or sensitive to small planetary differences. Above the frozen ground, Dragonfly will travel through golden air toward one quiet chemical landscape after another. Mars is placing carefully selected pieces of its history inside sealed tubes. NASA's Perseverance rover explores Jezero Crater, where an ancient river once entered a lake. The crater contains layers of rock shaped by water, sediment, volcanic activity, and later changes in the environment. Perseverance uses a drill to remove narrow cores from chosen rocks. Each core is placed inside a clean titanium tube. The tube is photographed, documented, and sealed against the Martian atmosphere. The rover also collects material from loose soil and samples of the atmosphere. Special witness tubes record any contamination that may come from the rover itself. These collections are designed for future study. The instruments carried by a rover must be small, light, and durable. Laboratories on Earth can use much larger equipment. They can repeat an experiment, prepare a sample in several ways, and apply techniques that may not exist when the rock is first collected. Returning Martian material would allow scientists to examine minerals at microscopic and atomic scales. They could search for complex organic molecules, unusual chemical ratios, fine layers, and structures that may record an ancient environment. The samples were not selected randomly. Mission scientists choose rocks that represent different parts of Jezero's history. Some formed through volcanic processes. Others contain sediments deposited by water. Sedimentary rocks can preserve delicate patterns because material settles gently in layers. A promising feature would still require careful interpretation. Minerals can grow into shapes that resemble biological structures. Organic molecules can arrive through meteorites or form through non-living reactions. The value of the sample lies partly in its context. Its exact location, surrounding geology, and relationship to other layers are all recorded. Inside each small tube rests a physical fragment of a world that once carried rivers across its surface. A returned sample would allow many laboratories to examine the same ancient stone. No spacecraft can carry every scientific instrument. A mission must choose a limited set of tools before it leaves Earth. Years may pass between the design of those tools and their arrival at another world. Earth laboratories are different. They can contain instruments larger than an entire rover. They can be upgraded as technology improves. Researchers can prepare extremely thin slices, separate individual minerals, and examine molecules with great precision. One laboratory may measure the ages of crystals, another may search for carbon-rich compounds, a third may study isotopes, which are forms of an element containing different numbers of neutrons. Living organisms often prefer lighter isotopes during chemical reactions. This preference can leave a pattern behind. Geological processes can also separate isotopes, so the measurement needs context. Microscopes may reveal textures too small for a rover camera. Chemical instruments may identify molecules present at extremely low concentrations. The same sample can be studied by independent teams. This independence is essential. Different methods may support one interpretation or expose a hidden problem. Returned material can also be preserved for future generations. Moon rocks collected during the Apollo missions continue producing discoveries decades later. New instruments reveal details that earlier laboratories could not measure. A Martian sample could have a similar scientific life. Only a small portion might be opened at first. The rest could remain sealed under carefully controlled conditions. A question not yet imagined may one day be answered by a grain collected many years earlier. In this way, sample return is not one experiment. It is a long conversation between a distant landscape and laboratories that continue learning how to listen. Planetary protection keeps the search from confusing Earth life with life from another world. Spacecraft are built by people in environments filled with microorganisms. Even clean rooms are not completely empty of life. Tiny cells and spores can rest on surfaces, tools, clothing, and particles of dust. A spacecraft sent to a potentially habitable world must therefore be cleaned and handled with great care. This is called forward planetary protection. Its scientific purpose is clear. If a lander detects an organism carried from Earth, the result could be mistaken for an alien discovery. Earth microbes might also enter an environment that future missions hope to study in its natural condition. Different destinations require different levels of protection. A mission passing a lifeless asteroid does not face the same concern as a spacecraft landing near possible water on Mars or sampling the plume of an ocean moon. Engineers use heat, chemicals, clean rooms, barriers, and strict procedures to reduce contamination. Some instruments carry witness materials that record what traveled with the spacecraft. Returning a sample creates a second responsibility. Backward planetary protection aims to prevent potentially harmful material from entering Earth's environment before it has been studied safely. No confirmed extraterrestrial organism is known. The precautions exist because uncertainty deserves preparation. A returned sample from a potentially habitable world would be sealed through its journey. It would enter a specialized facility designed to protect both the material and the surroundings. The sample must remain clean enough for science while also remaining contained. Planetary protection is sometimes described mainly as caution. It is also a form of respect. A distant environment should be encountered as it is, not quietly changed before its story can be understood. The cleanest search begins by making sure the evidence did not arrive from home. The James Webb Space Telescope is beginning to examine the chemistry of distant atmospheres. Webb does not travel toward exoplanets. It remains near Earth and gathers the light that has crossed interstellar space. When a planet transits its star, a small portion of the starlight passes through the atmosphere. Molecules absorb selected wavelengths before the light reaches the telescope. Webb separates that light into a spectrum. The resulting pattern can reveal gases such as water vapor, carbon dioxide, methane, or carbon monoxide. This work is especially effective for large planets with deep atmospheres. Their signals are stronger because more gas filters the starlight. Small rocky planets are much more difficult. Their atmospheres are thin, and their transit signals are faint. Clouds may hide deeper layers. Stellar activity can change the light in ways that resemble atmospheric features. Webb must observe some planets repeatedly. Many transits can be combined, gradually strengthening a pattern that remains hidden within noise during one observation. The telescope has already measured carbon-bearing molecules in exoplanet atmospheres. These discoveries reveal chemistry, not confirmed life. A planet can contain methane and carbon dioxide through ordinary physical processes. Even water vapor shows only that water exists somewhere in the atmosphere. It does not reveal an ocean or biosphere by itself. The value of Webb lies partly in learning how to make these measurements. Researchers test models against real atmospheres. They improve techniques for separating planetary light from the behavior of stars. Every atmosphere becomes a lesson for the next one. Across dozens of light years, Webb receives a few altered wavelengths and begins reconstructing the invisible air of another world. Direct imaging tries to separate a planet's light from the overwhelming brightness of its star. A distant Earth-like planet appears billions of times fainter than a Sun-like star in visible light. The two are also separated by a very small angle in the sky. From far away, Earth would be a pale point almost hidden inside the Sun's glare. Direct imaging requires the starlight to be suppressed. One method uses an instrument called a coronagraph. A coronagraph sits inside a telescope and blocks or redirects much of the star's light. Careful mirrors and masks reduce the bright pattern that would otherwise cover nearby planets. Another possible approach uses a star shade. A star shade would be a separate spacecraft shaped like a large flower. It would fly far in front of a telescope and block the star before the light enters the instrument. Its carefully designed edges would control diffraction, allowing the darker space around the star to be observed. Once a planet is separated, its own light can be analyzed. The color may reveal clouds, oceans, ice, rock, haze, or vegetation-like pigments. Changes over time may show rotation, weather, or seasons. A spectrum can reveal atmospheric gases. Direct imaging also allows planets with long orbits to be studied without waiting for them to transit. The method remains extremely demanding. Tiny imperfections in a mirror can scatter enough starlight to hide a planet. The telescope must remain stable with extraordinary precision. Years of engineering are needed to make darkness around a star dark enough. The desired prize is a point of light. Within that point may be oceans, continents, clouds, storms, chemistry, and perhaps biology. The Habitable Worlds Observatory is being designed around the search for nearby Earth-like planets. It remains an observatory in development rather than a completed spacecraft. Its central scientific goal is unusually direct. The mission is intended to identify and study potentially habitable worlds around nearby stars. NASA's current objective includes directly imaging at least 25 such planets. The observatory would operate at ultraviolet, visible, and near-infrared wavelengths. A large, stable mirror would gather light. Advanced starlight suppression would separate planets from their suns. The telescope would then use spectroscopy to study their atmospheres. A single world might reveal water vapor, oxygen, methane, carbon dioxide, and other gases. Its color could change as it rotates. Seasonal observations might show the movement of clouds or ice. The observatory would also study many other parts of the universe. A telescope capable of detecting an Earth-like planet beside a star would have the sensitivity to examine distant galaxies, interstellar gas, stars, and the wider history of cosmic structure. Its search for life would be part of a broader astronomical mission. The most important result may not come from one planet. A sample of many nearby worlds can reveal patterns. Researchers could compare planets around different stars. They could ask how often rocky worlds retain atmospheres and how frequently water-related chemistry appears. If one planet shows a compelling biosignature, it would become a target for repeated study. If none do, the result would also be meaningful. It would begin placing limits on how commonly nearby planets develop detectable biospheres. The observatory's task is to transform the question from possibility into statistics. Instead of studying one pale world in isolation, astronomy may begin comparing several neighboring planetary systems as a family. Ground-based telescopes will gather more light than many earlier observatories. The atmosphere above Earth blurs incoming starlight. It also absorbs selected wavelengths, yet the ground offers room for extremely large mirrors. Several next-generation observatories are being designed with mirrors measuring tens of meters across. A larger mirror collects more photons. It can study fainter objects and separate finer details. Adaptive optics helps correct atmospheric distortion. A telescope observes a bright reference point, measures how Earth's air bends the light, and rapidly changes the shape of a flexible mirror. These corrections occur many times each second. The result can approach the sharpness of a telescope above the atmosphere at certain wavelengths. Large ground-based instruments will measure exoplanet masses and atmospheres. They may search nearby rocky planets for gases and study the motion of clouds and winds on giant worlds. They can also use high-resolution spectroscopy. A planet's atmospheric lines move slightly because the planet is orbiting its star. The star's lines and Earth's own atmospheric lines move differently. By separating these patterns, astronomers may isolate a faint planetary signal. Ground and space observatories will work together. A space telescope may identify an interesting atmosphere, without interference from Earth's air. A large ground telescope may then study individual spectral lines with greater detail. Repeated observations across years can reveal changes. The future search will not depend on one perfect instrument. It will depend on a network of telescopes, each gathering a different part of the same distant light. A possible discovery of life will rise through levels of confidence rather than arriving as one sudden answer. Science has learned caution from earlier surprises. A gas may be announced as unusual, then later explained by chemistry. A microscopic shape may resemble a fossil, while minerals provide another origin. An instrument can create a pattern that disappears after recalibration. For this reason, researchers are developing frameworks for evaluating life detection evidence. The first level may simply identify a signal that could have biological importance. The next steps ask whether contamination and instrument errors have been excluded. Researchers then examine non-biological processes that might create the same result. Independent measurements become increasingly important. A possible biological molecule may be supported by a cellular structure. An isotope pattern may agree with the surrounding geology. A chemical imbalance may persist through repeated observations. The environment must make sense as a whole. Water, energy, nutrients, temperature, and stability do not prove life, but they help determine whether a biological explanation is plausible. Confidence grows when several different observations point in one direction and ordinary alternatives become less convincing. Language also matters. A preliminary result should not be described as final proof. Clear levels allow the public and scientific community to understand how far the evidence has progressed. The first report may therefore sound modest. It may describe a candidate biosignature, an unexplained chemical pattern, or a structure consistent with biology. Months or years of investigation may follow. The greatest discovery in biology may begin not with certainty, but with one careful sentence asking other laboratories to look again. Independent confirmation would turn an interesting signal into shared evidence. A telescope team may find an unusual atmospheric pattern. Another telescope should observe the same planet. Different instruments should detect the feature. Researchers using separate analysis methods should reach compatible results. For a physical sample, several laboratories would examine portions under controlled conditions. Some teams might be told which samples are real and which are blanks. Others may work without knowing, reducing unconscious expectations. The candidate must survive attempts to disprove it. This process can appear slow, but slowness protects the meaning of the result. A claim of life beyond Earth would affect astronomy, biology, philosophy, and humanity's understanding of its place in nature. The evidence must therefore be stronger than excitement. Confirmation may take different forms. Living cells in a sample could reproduce under controlled conditions. Molecules might show organized patterns too complex for known geology. Several gases in an exoplanet atmosphere might remain far from chemical balance. A repeating technological signal could carry structured information and remain fixed to a distant star. Different discoveries would require different standards. Microbial fossils would not be confirmed in the same way as radio communication. A subsurface ocean would demand other evidence than an atmospheric biosignature. The common principle is convergence. Many measurements, many observers, and many attempts at explanation must gather around the same conclusion. When certainty finally arrives, it may not feel like one dramatic moment. It may feel like a long series of careful doors closing until only one extraordinary path remains open. The first confirmed living world would begin a new era of questions. Finding microbial life nearby would allow direct comparison with Earth biology. Scientists would ask whether it uses DNA, proteins, carbon, and water. They would examine its molecular handedness and genetic relationships. Shared chemistry might suggest a common origin, or the natural preference of chemistry itself. Completely different biology would reveal that life can begin through more than one pathway. An atmospheric biosignature on a distant planet would leave the organisms themselves unseen. Researchers would study the world's seasons, surface colors, star, climate, and neighboring planets. New telescopes would return to it repeatedly. A technosignature would create still more questions. Its age would depend on distance. A signal arriving from 100 light-years away would show technology as it existed 1 century earlier. Communication would require patience. Even the nearest stellar exchange would unfold across years. A distant exchange could extend beyond individual lifetimes. The discovery would not complete the search. One living world would raise questions about frequency. A second would allow comparison. Many would reveal whether the galaxy contains common patterns or extraordinary diversity. The meaning of alone would also change. Humanity might remain separated by distance even after learning that life exists elsewhere. Knowledge would cross the gap before bodies or conversations ever could. The universe would feel both more inhabited and still immense. A confirmed biosphere would become one quiet light among the stars, carrying its own history, chemistry, and path through time. The search is becoming more precise, but it remains gentle and patient. Spacecraft are traveling toward icy moons. A flying laboratory is being prepared for Titan. Sealed pieces of Mars wait inside small tubes. Telescopes separate atmospheres into colored lines. Future observatories are being designed to see nearby planets directly. Each effort approaches the same question from a different direction. Some study places close enough to touch. Others study worlds that remain permanently beyond the reach of current spacecraft. Together, they reduce uncertainty one measurement at a time. There may be no single year when the universe changes from silent to inhabited. Instead, evidence may gather slowly. An ocean is confirmed beneath ice. A molecule appears in a plume. A distant atmosphere resists every ordinary explanation. Confidence rises through repeated observations until a possibility becomes difficult to deny. Or the searches may continue without a detection, teaching science where life does not appear and which environments remain quiet. Either outcome expands understanding. The search for life is also a study of planets, chemistry, stars, oceans, and time. It reveals how worlds form and why they become different. Long before an answer arrives, the question has already made the universe more detailed. Across laboratories, observatories, and spacecraft, matter from Earth is learning how to recognize life beneath another sky. The Milky Way may contain regions where habitable planets form more easily than in others. A star does not exist alone. It moves through a galaxy containing gas, dust, radiation, other stars, and the remains of ancient stellar explosions. These surroundings change gradually from one region to another. Near the center of the Milky Way, stars are packed more closely together. The region contains many heavy elements produced by earlier generations of stars. Astronomers call these elements metals, even when they are not metals in the ordinary sense. Carbon, oxygen, silicon, and iron all belong to this astronomical category. Planets need such material. Rocky worlds form from dust containing silicates, metals, carbon compounds, and other solid grains. Regions enriched by older stars may therefore provide abundant material for building planets. Yet the inner galaxy also has challenges. Stars pass closer to one another. Supernovae may occur more frequently. The central region contains energetic radiation and a supermassive black hole. Farther from the center, the environment becomes quieter, but heavy elements may be less abundant. This leads to the idea of a galactic habitable zone. Instead of describing a narrow ring with permanent boundaries, the concept explores a changing balance. A region must contain enough planet-forming material while avoiding excessive disruption. The exact location remains uncertain. Life may survive radiation more effectively than expected. Planetary atmospheres, oceans, magnetic fields, rock, and ice can all provide protection. A planet near the galactic center may remain habitable beneath a deep ocean. Another in the outer galaxy may form successfully despite having fewer heavy elements. Stars also travel. Over billions of years, their orbits can carry them through different parts of the Milky Way. A planetary system may not remain in the same galactic neighborhood throughout its history. Habitability, therefore, depends on more than distance from one star. Every living world, if others exist, also belongs to a wider landscape of slowly turning stars. Ancient planetary systems show that small worlds begin forming early in the history of the galaxy. Kepler 444 is an old star with 5 known planets. The system forms when the Milky Way is only about 2 billion years old. It is therefore far older than the solar system. Its planets are all smaller than Earth. They move in tight orbits, completing their years in fewer than 10 Earth days. These particular worlds are too close to their star to resemble a temperate Earth. Their importance lies in their age. They demonstrate that small rocky planets can form during an early period of galactic history. The universe does not wait for the sun before beginning to assemble solid worlds. Some old stars may therefore have planets that receive billions of additional years for geological and chemical change. A planet twice Earth's age could pass through many climates. Continents might rise and disappear. Oceans might gather, freeze, evaporate, and return. Life, if it begins, may experience an evolutionary history longer than the entire age of the solar system. Age alone does not guarantee complexity. A planet can become sterile early and remain that way. Its star may alter its atmosphere. Geological activity may stop. Water may be lost into space or locked permanently inside rock. An old biosphere may also remain microbial. Evolution has no obligation to produce intelligence simply because time is available. Still, ancient systems enlarge the possible timeline. A technological society elsewhere need not be only centuries or millennia older than humanity. Its world could begin forming while the galaxy itself still looks young. Such a civilization might disappear before Earth exists. It might remain active today. It might change into forms that current astronomy does not know how to identify. Around old stars, planets have been completing silent orbits for longer than the sun has been shining. Moons may provide as many possible habitats as planets. The solar system contains far more moons than major planets. Some are small, captured objects. Others are round worlds with atmospheres, volcanoes, ice, oceans, and complex geological histories. Europa, Ganymede, Enceladus, and Titan demonstrate that a moon can become one of the most interesting places in a planetary system. Similar moons are expected around exoplanets. Large planets form inside disks of material, and smaller bodies can gather around them. Other moons may be captured later through gravitational encounters. Detecting an exomoon is extremely difficult. A moon is smaller and fainter than its planet. It may slightly alter the timing or shape of the planet's transit. It may also produce a second, much shallower dip in starlight. Several possible exomoons have been reported, but confirming them remains challenging. Stellar changes, noise, and alternative planetary arrangements can imitate some of the same signals. Even without a confirmed population, moons are expected to be common from the processes seen in the solar system. A moon orbiting a giant planet inside a star's habitable zone may receive suitable warmth. Its planet could also provide tidal energy. As the moon's orbit changes under gravitational pulls, its interior may flex and release heat. Too much tidal heating could produce intense volcanic activity. A moderate amount might keep water moving beneath ice or support long-term geology. The giant planet could protect its moon from some impacts while also directing other objects inward. It may create radiation belts that challenge surface life. A large moon may retain an atmosphere and surface ocean. A smaller moon may shelter water below ground. From a distant telescope, such a habitat might be hidden beside the brighter image of its planet. Some living worlds may not circle stars directly. They may travel around planets, carried through each year as worlds within worlds. A planet can drift through the galaxy without belonging to any star. These objects are called rogue planets or free-floating planets. Some may form alone from collapsing clouds of gas. Others probably begin inside ordinary planetary systems. Young systems can be dynamically restless. Planets pull on one another. Giant worlds migrate. Close encounters alter orbits. In some cases, a planet receives enough speed to escape its star entirely. The world then enters interstellar space. Without nearby starlight, its surface becomes cold and dark. An Earth-like atmosphere may freeze. Open oceans would not remain beneath a mild sky. Yet the interior can stay warm. Radioactive elements inside rock release heat as they decay. A large planet also preserves energy left from its formation. If a rogue world contains a thick layer of ice, that ice can act as insulation. Liquid water may remain underneath for extremely long periods. A dense hydrogen atmosphere could also retain internal warmth in certain theoretical models. Such a planet would have no sunrise, seasons, or visible sun. Its surface may be covered by darkness and ice. Any possible life would depend on chemical energy. Water interacting with rock could produce hydrogen and other useful compounds. Hydrothermal environments might support microbial ecosystems beneath the frozen shell. No inhabited rogue planet is known. Even detecting the worlds themselves is difficult, because they reflect almost no starlight. Astronomers use gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity briefly bends and magnifies the background light. The event may last only hours or days, depending on the planet's mass and motion. NASA's Roman Space Telescope is expected to use this method to help count free-floating worlds. The galaxy may contain vast numbers of them. Between its visible stars, entire planets could be moving through the dark, carrying warmth inside, while leaving almost no light behind. Brown dwarfs occupy the quiet boundary between planets and stars. They are more massive than ordinary giant planets, but not massive enough to sustain the same hydrogen fusion that powers stars like the Sun. Brown dwarfs glow mainly through heat left from their formation. Young examples can be warm and relatively bright in infrared light. Over time, they cool and fade. Their atmospheres can contain clouds and changing weather. Some clouds may be formed from silicates or metals at high temperatures. Cooler brown dwarfs can contain water vapor, methane, and other molecules associated with giant planet atmospheres. A planet or moon could theoretically orbit a brown dwarf. Early in the system's history, the central object might provide substantial heat. As it cools, the region where surface water can remain liquid would move inward. A planet's climate would therefore face a changing energy supply. The habitable period may be limited, depending on the brown dwarf's mass and the planet's orbit. Close planets may also become tidally locked. Brown dwarfs can produce magnetic activity, radiation, and auroras, creating additional influences on nearby worlds. None of this makes such systems impossible habitats. Life could exist beneath a surface and rely partly on internal energy. A world might pass through a temporary warm era, long enough for chemistry to develop. Brown dwarfs are also useful laboratories for understanding planets. Some free-floating objects have masses and atmospheres close to those of giant exoplanets, but there is no bright star beside them. Their light can therefore be studied more directly. They reveal cloud layers, storms, molecular chemistry, and changing temperatures. Nature does not place a sharp visual boundary between a large planet and a small failed star. Across that gentle border, atmospheres continue forming clouds beneath faint infrared skies. Planets orbiting two stars show that stable worlds can exist beneath changing sunlight. These worlds are called circumbinary planets. They travel around both stars at once rather than belonging to only one member of the pair. From the planet's surface, two suns could move through the sky. Their apparent distance from one another would change as they orbit. One might pass in front of the other. The combined brightness could vary through complicated cycles. At first, such systems may seem too unstable for planets. Gravity from two moving stars creates a more complex environment than gravity from one. Yet planets have been discovered in stable circumbinary orbits. They usually remain far enough from the stars that the pair acts, from a distance, like one combined source of gravity. Their climates may receive changing amounts of energy as the stars move and the planet completes its wider orbit. An atmosphere and ocean could soften some of these variations. The traditional habitable zone becomes more complicated. Its boundaries depend on the brightness of both stars and their motion around each other. A giant circumbinary planet within that zone may not provide a solid surface. Large moons around it could become more interesting. Binary stars are common in the galaxy. Some pairs orbit closely, others are separated by great distances. In wide systems, a planet may circle one star, while the second appears as an unusually bright distant companion. Life beneath two suns would not require unfamiliar chemistry. It would simply develop under different rhythms of light, shadow, seasons, and gravity. Photosynthetic organisms might adapt to changes in color if the two stars have different temperatures. Biological clocks could follow several overlapping cycles. The sky of an inhabited world need not contain one steady sun. Nature can preserve stable oceans beneath light that rises in pairs. Interstellar objects show that solid material travels naturally between planetary systems. In 2017, astronomers discover Oumuamua, moving through the solar system on a path that is not bound to the Sun. In 2019, Comet 2I Borisov becomes the second confirmed interstellar visitor. A third known object, Comet 3I Atlas, is identified in Each comes from beyond the solar system. Their high speeds and open trajectories reveal that they do not remain in orbit around the Sun. They pass through and continue outward. Such objects are probably ejected during the formation and evolution of other planetary systems. Giant planets can scatter comets and asteroids. Passing stars can disturb distant reservoirs. Over time, countless fragments may be released into interstellar space. Most drift unseen. Occasionally, one crosses a region close enough to Earth for telescopes to notice. These visitors carry material formed around other stars. Their ice, dust, minerals, and organic compounds provide samples of planetary construction beyond the solar system, even when no spacecraft can catch them. They also demonstrate that material exchange occurs across interstellar distance. A rock ejected from one system may travel for millions or billions of years before entering another. Most never strike a planet. Some may become captured or collide with a moon, asteroid, or atmosphere. Whether living organisms could survive such a journey remains deeply uncertain. Radiation gradually damages molecules and cells. The travel time may be immense. Ejection and arrival introduce additional stress. A sufficiently large rock could shield material buried deep inside, but possibility is not evidence. The main discovery is quieter. Planetary systems are not perfectly sealed islands. They release pieces of themselves into the galaxy, and the space between stars contains wandering fragments of other suns. Panspermia moves the location of life's beginning, without explaining the beginning itself. The idea proposes that life, or material capable of becoming life, can travel from one world to another. Several versions exist. Within one planetary system, impact-ejected rocks might carry microorganisms between neighboring planets. This is called lithopanspermia. Comets and dust could transport organic material. A more speculative version imagines biological material crossing the distance between stars. The known movement of meteorites shows that planetary transfer is physically real. Rocks from Mars reach Earth. Impacts can launch material into space. Interstellar objects prove that some fragments escape their original stars. The biological part remains unconfirmed. An organism must survive ejection, radiation, cold, vacuum, time, atmospheric entry, and arrival in a suitable habitat. Some Earth organisms tolerate individual parts of this journey under laboratory or near-space conditions. Survival through the entire natural process is another question. Even a successful transfer would not reveal how life first begins. If Earth receives early organisms from Mars, another world, or an ancient parent system, biology still needs an original chemical origin somewhere. Panspermia changes the family tree. It may allow several planets to share one beginning. A solar system with life on multiple worlds would not necessarily contain multiple independent origins. This distinction matters. Finding Martian organisms with chemistry almost identical to Earth life could suggest common ancestry. Finding a completely different information system would point more strongly toward a separate beginning. Both discoveries would be profound. One would show that life can spread between worlds. The other would show that it can arise more than once. The universe may contain many living planets while holding fewer independent beginnings than appearances suggest. Life and worlds may travel together through a history larger than any single planet. A technological civilization may be almost invisible when observed only through its home planet. Earth's most detectable artificial signals are not all equal. Powerful radar can travel much farther than ordinary mobile communication. City lights are faint across interstellar distance. Atmospheric pollution is also difficult to measure from far away. A distant observer using instruments comparable to those now imagined for Earth might detect the biosphere before detecting civilization. Oxygen, methane, water, and seasonal surface changes could reveal a living planet. Technology might remain unseen. A civilization could also move much of its activity away from the planetary surface. Industry may take place on moons, asteroids, artificial habitats, or distant regions of the system. The home planet could retain an atmosphere resembling its pre-industrial state. Its night side may have little artificial light. Communication may travel through cables or narrow beams. Energy systems may release only modest waste heat. The system would contain advanced technology, while the inhabited planet appears naturally biological. This creates another limitation in the search. Astronomy often begins with planets because planets are visible and familiar. Intelligence may not remain concentrated where biology begins. Machines could operate in colder outer regions where heat is easier to radiate. Habitats might circle asteroids or remain hidden in the glare of a star. Small structures would be difficult to see from light years away. A society may also choose deliberately quiet technology, although no assumption about intention is needed. Efficiency alone reduces unintended signals. The absence of detectable industry does not prove the absence of intelligence. A green and cloud-covered planet may contain only microbes. It may also belong to a civilization whose brightest work occurs silently elsewhere in its system. Earth's own visibility has changed throughout its history. For most of the planet's existence, no technological signal leaves the solar system. Earlier Earth does not even display the same biological atmosphere seen today. Before oxygenic photosynthesis transforms the air, a distant observer may find little oxygen. Later, oxygen accumulates while complex organisms remain absent. Forests alter surface color only during a comparatively recent chapter. Artificial radio appears during the thinnest final moment. Earth is therefore not one unchanging target. Its detectability depends on when it is observed. A telescope viewing Earth from 1 billion light-years away would see a time long before animals appear. An observer 100 light-years away sees the planet as it was 100 years ago. This creates a wider lesson. A living exoplanet may be passing through an era with weak biosignatures. Its atmosphere may become more recognizable millions of years later. A civilization may already exist while its earliest signals remain in transit. Another may disappear while its radio waves continue traveling outward like an expanding memory. Planets and observations meet only at particular moments. A telescope receives a narrow sample from a much longer history. The absence of oxygen may describe a young biosphere rather than a lifeless world. The absence of technology may describe a civilization before radio or after it becomes quiet. Even a strong signal belongs to the past. The farther its source, the older the message. Across the galaxy, countless worlds may be visible during the wrong chapter for the evidence being sought. The search is therefore not only spread across space, it is spread across time, with every telescope looking backward through a different distance. The question of whether humanity is alone may not have one simple scale. Earth may be the only inhabited world in the solar system. While belonging to a galaxy rich in microbes, the Milky Way may contain many biospheres, but very few technological societies. Technology may be common across cosmic history, while rarely overlapping in time. Life may exist beneath the ice of rogue planets, on moons beside giant worlds, or inside regions that no telescope can study from afar. Some organisms may be close enough for spacecraft to sample. Others may remain separated by distances that no living traveler can cross. The word alone can therefore describe several different conditions. A planet can be biologically unique. A species can be the only one capable of asking questions in its local region. A civilization can know that others exist while remaining unable to exchange a conversation. Knowledge can end one kind of isolation without ending distance. Science does not yet know which version describes Earth. What it does reveal is that possible habitats are more varied than the first simple pictures suggest. They do not all require blue skies and warm continents. They may exist beneath ice, inside rock, around two stars, around old stars, or without a star at all. The galaxy holds many ways for a world to remain warm, chemically active and stable. Whether matter becomes alive in those places remains the central uncertainty. Every new category enlarges the map without filling it. Beyond the familiar planets, the universe continues offering quiet rooms where life might have begun unseen. The most honest answer is that science does not yet know whether humanity is alone. The universe contains an extraordinary number of stars and planets. Water, carbon, and organic chemistry appear throughout space. Several nearby moons contain hidden oceans. Ancient Mars once held rivers and lakes. These discoveries show that the ingredients associated with life are not limited to Earth. They do not show that those ingredients have become alive elsewhere. Only one planet is known to contain organisms. Every microbe, tree, whale, insect, and person belongs to the same confirmed biosphere. This leaves the central probability almost completely unknown. Life may begin easily when water, chemistry, energy, and stability come together. If so, countless planets and moons may contain living cells. Life may require a very unusual sequence of events. In that case, many worlds could remain habitable but empty. The evidence currently allows both possibilities. Astronomy can estimate the number of planets. Chemistry can reveal which molecules form naturally. Biology can explain how known organisms survive and evolve. None of these fields can yet calculate the exact likelihood that lifeless chemistry becomes biology. The uncertainty is not a weakness. It is an accurate description of the frontier. Science often begins with a question that cannot yet be answered. Instruments improve, new places are explored, explanations are tested and refined. The unknown gradually becomes smaller. Humanity is not standing before an empty wall. It is standing before a landscape that is only beginning to come into view. Stars have become planetary systems. Points of light have become worlds with atmospheres. clouds, oceans, and changing seasons. The final answer remains hidden among them. For now, the universe is neither confirmed to be crowded nor confirmed to be empty. It remains wonderfully open. One example of life cannot reveal how common life is. Earth provides an enormous amount of biological information. It shows that cells can arise on a rocky planet with liquid water. It shows that evolution can produce photosynthesis, multicellular organisms, nervous systems, intelligence, and technology. Yet all known organisms appear to share one deep ancestry. They use related genetic systems. They build proteins from the same broad molecular language. Their cells perform many of the same fundamental tasks. Earth may therefore represent one experiment rather than billions of independent experiments. A forest contains many species, but it does not provide many separate origins of life. Every branch grows from the same ancient root. This creates a statistical difficulty. Imagine finding one stone on a distant beach. The stone cannot reveal whether every beach contains similar stones. It cannot show whether the object is ordinary or remarkably rare. More examples are needed. The discovery of independent life on Mars, Europa, Enceladus, or another nearby world would immediately change the picture. If life begins twice within one solar system, the process may be relatively common when conditions are suitable. If every explored habitat remains sterile, the result would not prove that Earth is unique. It would suggest that suitable chemistry alone does not guarantee biology. The most informative discovery may therefore be a second origin. It does not need to be intelligent. It does not need to be complex. One cell with a separate molecular history would transform the understanding of life throughout the cosmos. Until such an example is found, every estimate rests partly on assumptions. Earth is both a rich library and a very small sample. The search continues because one living world is enough to show that life is possible, but not enough to show how often possibility becomes reality. Simple life may be much more common than complex life. Microorganisms dominate Earth's biological history. They appear early and remain present through every major environmental change. They live in oceans, soil, clouds, rocks, ice, and hot underground water. They require no forests, skeletons, cities, or machines. A microbial biosphere can remain almost invisible from interstellar distance. It may produce only subtle atmospheric changes. If it lives beneath ice or underground, it may alter the surface very little. Such life could occupy numerous worlds without creating signals that present telescopes can detect. Ocean moons are especially interesting in this way. A hidden sea may provide liquid water, minerals, and chemical energy for billions of years. Microbes could live near the seafloor, while the frozen surface remains pale and quiet. No radio waves would emerge. No artificial lights would shine. Even atmospheric biosignatures might be absent, because the ocean is sealed beneath ice. The solar system could theoretically contain a second biosphere that has remained nearby and unseen throughout human history. The same may be true across the galaxy. A planet with surface oceans may host only microscopic organisms. Another may contain biological films around warm springs. A rogue planet may shelter slow metabolism beneath a frozen shell. These living places would answer one great question while leaving another open. Life may be widespread without intelligence being widespread. The universe could contain countless cells and very few minds capable of studying the stars. A silent galaxy is therefore not necessarily a lifeless galaxy. Its most common inhabitants may be too small, too deep, and too quiet to announce themselves across space. Complex life may depend on long periods of planetary stability. Earth's history contains many changes. Continents move. Volcanoes alter the atmosphere. Ice spreads and retreats. Asteroids strike. Species appear, diversify, and disappear. Life survives these changes, but complex ecosystems require time to rebuild. A planet must remain suitable long enough for many evolutionary steps to occur. Its star should provide reasonably stable energy. Its atmosphere must avoid disappearing completely. Liquid environments need to persist or return. Geology may also play an important role. On Earth, moving crust recycles carbon and minerals. Volcanoes return gases to the atmosphere. Weathering removes carbon dioxide from the air. These processes help regulate climate across long periods. A planet without plate tectonics might still remain habitable through other mechanisms. The exact role of Earth's geology is still being studied. Large moons, magnetic fields, continents, oceans, and planetary rotation may all influence stability without acting as absolute requirements. There may be many ways to maintain a biosphere. Still, Complex organisms need more than one mild afternoon in planetary history. They need environments that remain useful across immense spans of time. A world may begin with oceans and later lose them. Another may spend most of its history frozen before entering a warmer era. Life could begin during a favorable period and disappear when conditions change. The galaxy may contain planets that once lived and now preserve only chemical or fossil traces. It may also contain worlds where complexity is only beginning. When a telescope observes one distant planet, it sees one moment within a much longer story. That moment may arrive before life, during life, or long after life has faded. Intelligence may be one rare branch among many successful forms of evolution. Evolution does not move toward a predetermined goal. It does not attempt to create language, science, or technology. Traits spread when they help organisms survive and reproduce within particular environments. A shell can be as successful as a brain. A slow metabolism can be more useful than curiosity. A stable microbial community may continue longer than any complex civilization. Human intelligence emerges through a unique history of climate, anatomy, social behavior, language, and chance. Other worlds would have different histories. An ocean planet might develop highly capable creatures without fire or metallurgy. A dense atmosphere might favor floating organisms with senses unlike those of land animals. A stable world may produce complex ecosystems but little pressure for technological change. Even when intelligence appears, it may follow unfamiliar directions. Another species might develop detailed communication, memory, and culture without building machines. It might study its environment through biological senses rather than manufactured instruments. Technology itself can take many forms. It may develop slowly. It may remain local. It may become efficient enough to release almost no detectable energy. The path from life to a radio telescope is therefore not automatic. It contains many transitions, each shaped by environment and chance. Humanity should not imagine itself as the final destination of evolution. It is one result of one planetary history. Elsewhere, matter may have learned to sense, remember, communicate, and wander through paths that Earth never explored. Another civilization may already be visible only as ancient light. Every astronomical observation looks into the past. The moon is seen as it appeared a little more than 1 second earlier. The sun is seen several minutes in the past. Nearby stars are seen years earlier. More distant regions of the galaxy appear centuries or millennia behind their present condition. A technosignature arriving today may have been transmitted before modern astronomy existed. Its source may still be active, or it may have changed completely. This delay makes the galaxy a collection of overlapping histories. A civilization could detect Earth's atmosphere from far away, while seeing a period before industrial technology. Another observer, much farther away, might see Earth before complex animals. Humanity also receives different chapters from different planets. A world 50 light-years away is observed as it was 50 years ago. A world 1,000 light-years away is seen 1,000 years in the past. No telescope can reveal their present condition immediately. Communication would unfold within the same delay. A message sent to a star 20 light-years away takes 20 years to arrive. A response requires another 20 years. The simplest exchange would extend across decades. At greater distances, a conversation might continue across many human generations. This does not make communication meaningless. It changes communication into something patient. A message may be created for recipients who are not yet born. A reply may be received by descendants of the original senders. Interstellar contact would connect histories rather than moments. The galaxy may already contain such messages moving silently between stars. Some may never cross Earth. Others may arrive before instruments are ready. A few may still be traveling toward the solar system, carrying information from a world that has not yet entered humanity's sky. Silence may reflect distance more than absence. The human search has lasted for only a brief time. Radio astronomy is young compared with the age of the galaxy. Exoplanet science is younger still. The first confirmed planets around ordinary stars were discovered only recently within the history of science. Before then, humanity did not know whether planetary systems were common. Now thousands of exoplanets are known, and statistics suggest that planets are a natural part of star formation. This transformation occurs within a few decades. Life detection remains at an earlier stage. Only a small number of worlds have been studied closely. Most exoplanet atmospheres remain beyond detailed measurement. Vast regions of the radio spectrum and sky have received little observation. Telescopes also listen for limited periods. A star may be observed for minutes or hours, then not examined again for months or years. A civilization transmitting intermittently could easily remain unnoticed. The situation resembles entering a quiet forest, listening briefly beside one tree, and concluding very little about the entire landscape. The forest may contain no voices. It may also contain signals too faint, too distant, or too infrequent for one short visit. As instruments improve, the listening becomes deeper. Surveys cover more stars. Computers examine wider frequency ranges. Space telescopes study smaller planets. Missions approach hidden oceans. The silence becomes more meaningful, only as the search becomes more complete. Humanity has not listened long enough to describe the entire galaxy. It has only begun learning which kinds of silence can be measured. The first discovery may appear ambiguous before it becomes convincing. A spacecraft may detect an unusual molecule in a plume. A telescope may observe gases in an exoplanet atmosphere that seem difficult to explain. A microscope may reveal structures inside Martian rock. None of these observations would automatically become proof. Natural chemistry is inventive. Minerals grow into delicate patterns. Radiation changes molecules. Geological processes create gases that can resemble biological products. Instruments also have limits. A weak signal may be distorted by noise. A sample can be contaminated. A computer model may omit an important reaction. The first announcement may therefore use careful language. Researchers may describe a possible biosignature or an unexplained chemical pattern. Other teams would examine the data. New observations would be requested. Alternative explanations would be developed and tested. The evidence might fade under closer inspection. It might also become stronger. A second instrument may detect the same pattern. A related molecule may appear. The surrounding environment may support the biological interpretation. Confidence would grow step by step. This gradual process protects the discovery. Life beyond Earth would be too important to rest on one uncertain measurement. The strongest conclusion would emerge when geology, chemistry, biology, and astronomy all support the same explanation. The first sign may be quiet. Its meaning may take years to understand. Eventually, a collection of small observations could become the first confirmed evidence that Earth is not the only living world. Discovering no life nearby would also teach science something important. Mars, Europa, Enceladus, Titan, and other worlds preserve different combinations of water, chemistry, and energy. If extensive exploration finds no organisms, researchers would examine why. Perhaps life needs surface cycles of sunlight, air, land, and ocean. Perhaps hidden seas lack some essential ingredient. Perhaps biology begins rarely, even in favorable environments. Each empty habitat would refine the conditions associated with life. A sterile Europa would remain a remarkable ocean world. An uninhabited ancient Mars would still reveal how a planet loses rivers, lakes, and atmosphere. Astrobiology does not lose value when life is absent. The same missions explain how planets work. They reveal the movement of ice, the chemistry of atmospheres, the origin of organic molecules, and the internal heat of moons. Absence can become evidence when a place is studied thoroughly. If many apparently suitable worlds remain lifeless, Earth's biosphere may appear increasingly unusual. That would not make the universe less beautiful. It would make the living surface of Earth even more significant. Every cell would belong to a rare planetary event. Every forest and ocean would represent a form of organization not yet found elsewhere. The search carries meaning in both directions. A discovery would enlarge the family of life. Continued silence would deepen appreciation for the one living world already known. Earth is not an ordinary place, simply because it is familiar. Its oceans continuously exchange water with the atmosphere. Clouds gather and dissolve. Rivers carry minerals toward the sea. Plants draw carbon from the air. Microorganisms transform soil and stone. Life occupies almost every suitable environment. It grows in warm sunlight and beneath polar ice. It lives around deep-sea vents, within desert rocks, and far below the ground. From orbit, biology changes the color and chemistry of the planet. Oxygen fills the atmosphere because living organisms continually replace it. Methane persists partly because biological processes release it. Green pigments cover broad regions of land. Microscopic ocean life influences clouds, gases, and global cycles. Earth is not simply a rock carrying separate organisms. It is a planet deeply altered by life. The biosphere interacts with air, water, and geology as one immense connected system. No other confirmed world displays this combination. Mars has weather, but no known ecosystem. Venus has clouds, but no confirmed biology. Europa has water, but no detected organism. The exoplanets remain distant points with uncertain surfaces and atmospheres. Earth is therefore the most complete living world that science can study. It provides the reference for every search elsewhere. Its chemistry teaches instruments what to measure. Its extremophiles expand the range of possible habitats. Its history shows that a biosphere can change dramatically over time. The search among the stars begins with attention to the ground beneath human feet. Before life is found elsewhere, one planet already demonstrates what matter can become. The atoms of Earth have learned to grow, adapt, remember, and look back toward the universe from which they came. The search for other life is also a search for understanding of Earth. Studying Venus reveals how climate can transform a neighboring planet. Mars preserves a record of water that disappeared from its surface. Ocean moons show that liquid water can remain hidden far from sunlight. Exoplanets reveal that the solar system is only one arrangement among many. Each comparison makes Earth's history clearer. Its atmosphere is not inevitable. Its oceans are not guaranteed. Its stable conditions emerge from a long interaction of star, orbit, geology, water, and life. Astrobiology joins many sciences because life cannot be separated from its environment. A cell depends on chemistry. Chemistry depends on temperature and pressure. Climate depends on atmosphere, oceans, land, orbit, and starlight. The question of alien life therefore leads back toward basic questions about planets. How does water arrive? How do atmospheres survive? How does chemistry become organized? How does a planet remain habitable while its star gradually changes? These questions matter even if no second biosphere is found. They reveal how fragile and resilient living systems can be. They may also help humanity care for the environment already available. Earth does not require comparison with another inhabited world to possess value. Yet the search places the planet within a wider cosmic setting. It shows a small blue world surrounded by many possibilities and no confirmed replacement. Looking outward encourages a gentler understanding of home. The same universe that forms galaxies and stars also forms rainfall, cells, memory, and thought on at least one quiet planet. Humanity may never physically visit a living exoplanet. The distances between stars are immense. Even the nearest neighboring systems lie far beyond the practical reach of present spacecraft. A probe traveling at current interplanetary speeds would require thousands of years to reach another star. Future propulsion may shorten the journey. Small robotic craft could travel faster than large crewed vessels. Still, interstellar exploration will remain demanding. Remote observation may therefore provide the first evidence. A spectrum may reveal an atmosphere transformed by life. A radio telescope may detect a structured signal. A future instrument may separate the surface colors of a distant planet. Knowledge can cross the distance even when travelers cannot. This has always been one of astronomy's quiet powers. Human beings have never visited the sun, stars, or distant galaxies. Their light still allows science to learn their composition, temperature, motion, and history. Alien life may be studied in the same way. Its planet may remain a point of light, yet that point could reveal water, seasons, gases, clouds, and biological activity. A confirmed biosignature would create a relationship based on observation rather than contact. Humanity would know that another living history is unfolding beneath another sky. The organisms themselves might never know that Earth exists. Distance would remain, but solitude would change. The universe would contain at least two places where matter has become capable of metabolism, reproduction, and evolution. A faint spectrum could therefore carry one of the deepest forms of connection available across space. A message from another civilization would connect two independent histories. The message may be simple. It could contain mathematical pulses, a repeating pattern, or information describing its source. It might also be unintended, discovered through radar, energy use, or another technological effect. The first task would be confirmation. Observatories around Earth would point toward the same region. Different instruments would examine the signal. Researchers would test satellites, aircraft, transmitters, and natural astronomical sources. If the signal remained tied to a distant star and carried structured information, the meaning of the night sky would change. Understanding the message could take much longer. A shared language would not exist. Mathematics, physics, and astronomy may offer common reference points. The properties of atoms and light are the same throughout the observable universe. More complex ideas would require carefully built definitions. The source's distance would also shape every exchange. A nearby message might allow a reply within decades. A distant one might make direct conversation impossible on ordinary human timescales. The value would not depend entirely on speed. The existence of one other technological society would reveal that intelligence and science can emerge independently. Humanity would become one participant in a larger natural possibility. The message would come from a world with its own oceans or deserts, its own evolutionary history, and its own way of dividing experience into meaning. Even one quiet pattern could show that the universe has produced more than one place capable of wondering about itself. Silence and discovery both require humility. Humanity has occupied only a small moment in cosmic history. Modern science has existed for an even smaller moment. The tools capable of studying exoplanets and technosignatures are very new. It is too early to treat silence as a final conclusion. It is also too early to treat probability as discovery. A universe containing many planets may still produce very little life. A universe rich in microbes may produce little technology. For this moment, it is enough to rest on the one living world already known. Earth turns softly beneath you. Its atmosphere holds close. Its oceans move in long, gentle rhythms. Life continues in forests, deep water, warm soil, and places no human eye has ever seen. And if you are still awake and would like to keep drifting, another quiet journey is waiting for you on screen. If these calm nights bring you a little peace, you are always welcome to return and wander gently through the cosmos again, one drifting mind at a time. Sleep well, and good night.